Okay, welcome everyone to this episode of the Cartesian Cafe. Today, we're very lucky to have John Baez with us. John Baez is a mathematical physicist. He is also a professor of mathematics at UC Riverside and a researcher at the Center for Quantum Technologies in Singapore, and also a researcher at the Topos Institute in Berkeley, California. John has worked on an impressively wide range of topics, including loop quantum gravity, applications of higher categories to physics, applied category theory, environmental issues and math related to engineering and biology, and most recently on applying network theory to scientific software. Additionally, John is a prolific writer and blogger. This first began with John's column, This Week's Finds in Mathematical Physics, which ran 300 issues between 1993 and 2010, which then continued in the form of his ongoing blog, Azimuth. Last but not least, John is also a host and contributor of the popular blog, The N Category Cafe, which to my knowledge is the original math-oriented cafe that well predates our current venue here at the Cartesian Cafe. Welcome, John. How are you today?
Great. It's good to be here. It's nice to go to a different cafe.
Yeah, indeed. It's always nice to have some variety in our life.
Mhm.
Yeah, you have a very diverse set of interests and background. Specifically, your interest, say, in physics. From personal experience, it's quite rare to find a mathematician that's well versed in physics. I think the only other person I could think of that's comparable is the great Isidore Singer, who sadly passed away recently.
Uh-huh.
You did your PhD at MIT, so you must have known Is. But maybe can you say more about your interest in physics and how you came to become multilingual in both math and
Mhm.
physics, and subsequently all the other things you've become interested in?
Yeah, I got interested in physics at an early age because my uncle, who's the father of the folk singer Joan Baez, was a physicist, and he was actually specializing in physics education. And so he would have all sorts of things in his suitcase when he'd come by, like lasers or diffraction gratings, and teach me physics that way, starting when I was quite young. So it seemed really exciting to me from an early stage. And then he gave me his college physics textbook when I was about 8, and I started trying to understand it. And so I wasn't so interested in mathematics at that early stage because it was all about adding and multiplying and so on. It didn't seem all that exciting. And so I actually, at some point, my parents were worried that I was so interested in physics, but I wasn't good enough at math. And they heard that like physicists have to be good at math to prosper. But later on, I started learning that on the one hand, it was really hard for me to do experiments that were at all interesting. So I was like really frustrated reading about people with cyclotrons and discovering fundamental particles and things like that because I couldn't do any of that stuff. And I'm not naturally an experimentalist. Someone who's really good at experiments would have figured out something fun to do. But I realized I could do things just with pencil and paper once I got to the point where I could like uh, do some physics type calculations. And so then my interest shifted more and more over towards math because that was something I could do just sitting there. Uh, and then by the time I went to college, the lab courses in physics that I would have that I had to take, and I would have had to take more if I majored in physics, those were so frustrating for me because I wasn't very good at them and the equipment wouldn't work and stuff like that, that I decided for that and other reasons that going into math would be better. By that point, I was already sort of 50-50. So I majored in math and I got a PhD in math, but I was always wanting to do physics with the math, or at least certainly in that era. And so I did my PhD with uh, Irving Siegel, who's actually the advisor of Isidore Singer. He was also at MIT, and he had been working on trying to make quantum field theory mathematically rigorous since the 70s. And so I got a sort of balanced outlook on math and physics, although I'm more comfortable when things are mathematically rigorous a little bit. Not as some mathematicians just can't stand the lack of rigor of physics, but I took enough physics classes that I sort of got the hang of that. And I now that I'm just thinking back on it all, or now that I'm not having to like decide what courses I'm gonna take or anything like that, I really appreciate the flexibility of the physicist's way of thinking. And sometimes I think mathematicians are a little too stuffy. So anyway, but sometimes I think the opposite, right? Sometimes I think physicists are too sloppy. So anyway, so it's fun to bounce back and forth is what I'm trying to say. And I've managed to insult both sides equally well.
Nice. And then, but you've also gone on to do other diverse things. Like maybe can you say a little bit about your work in, I think, environmental issues? I think maybe, is it specifically carbon emissions, or is it, does it encompass other things? Yeah.
It encompasses other things. So starting roughly around 2008, I started getting really worried about climate change and started reading a lot about it, and learned that it was just part of a much bigger set of issues called the Anthropocene, where humans are really affecting the parameters of the biosphere in a lot of ways. Just like for one example, like most of the nitrogen taken out of the atmosphere now is not taken out by plants the way it used to be, but taken out by humans in this Haber-Bosch process for making fertilizer. And we put take much more phosphorus out of the earth than any natural process. So we're basically sort of dominating the biosphere, and we're sort of going about it in a unthinking way, locally just trying to maximize economic production. And it's leading us into all sorts of problems, of which climate change is sort of the most famous one and a very serious one. So I started wanting to have something to do with that. And I floundered around. So I went to the Center for Quantum Technologies in Singapore, and that was a really nice time from 2010 to 2012, where I was just able to do research. And so I spent that time sort of trying to regroove my career a little bit, motivated by this climate change issue. But ultimately, it settled out a few years later that what I was doing was trying to get mathematicians, especially category theorists, to start applying their talents to practical issues like climate change, but not at all limited to that. Because I was big on this branch of math called category theory, so I had some ability to influence the mathematicians in that branch of math. And it's famous for being an unapplied area, or at least it's applied to math all the time, but not, when people talk about applied mathematics, they're talking about like solving, quote, real world problems, and people didn't tend to associate category theory with that. But I've been trying to convince people that it actually is good for that. And so then recently, like in the last couple of years, a project involving epidemiology and making models of epidemics came up. Not so much because of COVID, although you might think it was that, but actually because an old college friend of mine, Nathaniel Osgood, grad school friend of mine, turned out to be heading the Canada's effort, or I don't know if he's heading it, but he's big in Canada's effort to model COVID, and he's a computer scientist. And so he got really interested in this applied category theory stuff. And so together with a bunch of people at the Topos Institute and his student Nguyen, we've been working on making software for epidemic modeling using applied category theory ideas. So that's been really exciting.
Oh, wow. So many topics. Well, and we're only going to focus on a small slice of that today. Unfortunately, I wish we could go into all those interesting things. Actually, another thing I wanted to ask you about is something you're also famous for. So I think it was 1992, so quite a while ago, that you came out with your crackpot index. I wanted to ask you how you came up with that. What motivated it? So I guess I guess people can kind of already maybe infer what it is, but maybe you should explain it yourself.
Sure. Yeah. So what happened was in the late 80s, I started discovering the internet along with a bunch of other people. And there were these, this is before the World Wide Web, and there were these things called called Usenet news groups, which were a way of communicating, chatting about subjects. And a whole bunch of physicists started chatting about physics. And then by the early 90s, it had become well known enough that non-physicists started getting in on this physics discussion group, and it included a bunch of people with far out theories of physics who previously would mainly communicate to physicists by like sending them letters with their theories and things like that. But now they discovered that they could just like hop onto these, it's like an old version of a chat room or something like that, hop onto these Usenet news groups and start propounding their theories. And that came as a big surprise to the physicists there, because all this stuff was brand new, and we were happily discussing advanced physics. And then someone says that like, oh, the solar system is a plutonium atom. And you tell them, no, it's not. And they would like argue and on and on and on in favor of their theory. And so I started learning a lot more about what I'll unpolitely call crackpot physicists at that time. And I discovered that there were a whole bunch of sort of standard behavior patterns among these people, which are more complicated and interesting than just that they happen to have some wrong theories. There's sort of like a whole ideology of being a crackpot. And so sort of partially as a joke, but also to sort of note my observations, I created this thing called the crackpot index, which lists a whole bunch of symptoms of being a crackpot and gives you points for different symptoms, with more points for more pronounced crackpotism, because I think there's like a progression of crackpotism. And so like near the end, you may be fantasizing about show trials where like finally your theory has been proved true, and you put all the physicists who didn't believe you on trial and force them to like admit that they were like deliberately holding up the progress of physics and things like that. That's a very extreme. That's like near the extreme end there.
I see. Yeah, I was actually, impressed by how quantitatively precise the index is. So let me just read like a few snippets here, just so people get an idea. So I'm just going to pick two right now. So item 21 is 20 points for suggesting that you deserve a Nobel Prize, and item 34 is 40 points for claiming that the scientific establishment is engaged in a conspiracy to prevent your work from gaining its well-deserved fame or such like. How did you decide on, what's 20 points, what's 40 points? Did you kind of like, is there some first principles here, or is there like maybe this person is a crackpot worth 100 points, so I have to kind of work backwards in such a way that they get 100 points? I mean, what's the formula?
It's not as quantitative as it's made out to be. I think the most important thing is the larger numbers indicate further progress towards a kind of extreme crackpotism. So the way it tends to work is like, first you have this idea, then you start developing it, you put more and more time in it. At first you think it's really great, and then you like start telling people about it, hoping that like they'll say, hey, that's a great idea. And then you like slowly learn that like all physicists make fun of you, or just don't ignore you. And then you start making up more and more complicated theories for why that's going on. And so it's sort of, I mean, of course, people can turn off the road at any point, and probably most people do. I mean, most people, if they get negative feedback from the physics community, they may like stop working on physics. But the true crackpots are the people who are completely convinced they're right, and so they have to make up more and more elaborate theories about why no one else seems to agree with them. And so those types of items get the larger numbers.
I see. Yeah, I think what's quite impressive about this list is it was made back in 92. So 3 decades ago, well predating any modern or modern crackpot or anyone in recent memory. So it seems to have been quite a, I guess, maybe robust index in some sense.
Yeah, probably.
Yeah. So I just to close the loop on this, that the reason I surfaced this crackpot index is that there seems to be actually a renaissance as of late in terms of evaluating so-called crackpots. So last year I went on several podcasts, one of which is called Decoding the Gurus, and there they deconstruct so-called gurus along their own gurometer scale. And then I also went on Robert Wright's show, where our episode was quite straightforwardly titled, "Is Eric Weinstein a Crackpot?" And just to get give some context about that, so the topics of those podcasts were about my rebuttal of an attempt at a theory of everything called geometric unity, which was put forth by a Harvard math PhD, Eric Weinstein. And he introduced this work to the world back in 2013 at Oxford through the Simony lectures. The work has been endorsed in the academic community by Professor Brian Keating at UC San Diego, who's performing experimental tests through a scholar in residence at UCSD. Anyways, so for the people who want to learn more about this work, they can check out those podcasts and others. But the interesting outcome of this is that both of those podcast hosts have their own so-called crackpot axes that they've evaluated certain people on. The Decoding the Gurus, in fact, Eric Weinstein and his brother are at the very top of their guru leaderboards. For Robert Wright's podcast, actually his conclusion at the end, after our episode and in his Substack article afterwards, was that Eric Weinstein was not a crackpot. But in any case, thanks to your index, now everyone has a very precise scale by which to evaluate any proposed theory of everything, whether it's how far it is along the crackpot spectrum. So anyway, so it's nice that you have like a very nice formula for all this.
Sometimes I get emails from people who tell me their own crackpot score, which I find quite surprising. And they say like, well, even though my score is like a 60, I still would like to talk to you about this stuff I'm doing.
Wow. That's I guess
it actually attracts crackpots to communicate with me. Some of them are very angry. They say like, this is like a terrible thing. This thing I did, it's like holding back the progress of science. But others like take a more humorous attitude towards it and don't seem too fazed by it. But if I'd wanted to like not be dealing with crackpots, I would have taken down the crackpot.
I see. Okay.
I thought you might think of it like repel crackpots, but it's not. It's like waving a red flag in front of a bull, basically.
Oh, I see. Kind of like even if I'm a crackpot, at least we can now openly discuss it because it's now not taboo, I suppose, because you're.
I don't quite get the psychology, but yeah.
I see. Great. All right. Well, thanks for entertaining me with this crackpot index. Anyway, so maybe we should start diving into the main focus of today's
sure. I'll tell you
discussion.
my own crazy theory.
Okay, that's right. Well, okay. I guess we'll see what that means later on.
I won't.
Oh, I see. Okay. Yeah. So basically, we're going to talk about aspects of the standard model. You wrote a paper with John Huerta explaining the mathematics behind the standard model and summarized basically its properties and representation theory, and also various so-called grand unified theories, at least insofar as their representation theory can be characterized. Do you want to say anything about that before we get started, and maybe why you wrote the paper and to what extent how to think about the math versus whatever speculative physics is maybe left untouched by your work?
Sure. Yeah. So it was meant to do a couple of things. So it was meant to be like an introduction to a small piece of particle physics for a mathematician. So it's written in a way that would be pretty hard to understand if you hadn't studied a fair amount of math. But for mathematicians, I think it's pretty easy to read, and it's only tackling a very limited part of particle physics. So like you will not come out of that knowing how to calculate the scattering cross-section of electron scattering. It doesn't explain quantum field theory, which is like fundamental to particle physics. It doesn't explain the Higgs mechanism, which is fundamental to the Standard Model. And there's lots of other things it doesn't explain. So it just focuses on the symmetry group of the Standard Model, the so-called gauge group of the Standard Model, and then how the different matter particles, primarily the so-called fermions, are acted on by these symmetries, because that's like a bite-sized piece of mathematics that mathematicians can get into, and it's already pretty interesting and complicated. And then it turns out that people who are trying to develop grand unified theories, which are like more advanced and more speculative theories that try to unify the different forces, they need to know this stuff cold, and then they try to look at the patterns in the Standard Model and sort of make up a theory that will explain those or neaten them up, make them more unified in some way. Because at first the Standard Model can look like a big pile of sort of arbitrary data. And so it turns out that there's a very beautiful pattern in the fermions or matter particles of the Standard Model, which is not at all obvious and really striking. And pretty much all grand unified theories try to make use of that or take advantage of that to neaten up the Standard Model. And so in our paper, we discuss just a little bit about 3 different grand unified theories that try to take the Standard Model symmetry group and put it in a bigger group. And then using the information about how the particles transform under the Standard Model symmetry group, we see how, oh, look, you can unify those particles into sort of fewer kinds of particles if you think of them as transforming under some bigger symmetry group. And the math of that is all very beautiful and nice. So that's what we try to explain, but there's like all sorts of things we don't explain about grand unified theories. So in particular, like the stuff calculations you'd need to do to see if those grand unified theories actually had a chance of being correct, but we don't actually get into that too much. So it has a limited goal.
If we go in the order of your paper, right, there's sort of like the nucleons and protons, and then maybe the description of all the different parts of the Standard Model, and then finally the different kinds of theories. Should we go chronological, or should we actually, let me talk a little bit about what the Standard Model is?
I'm sort of flexible. Maybe I'll just say like a minute of stuff, get oriented here. So once upon a time, people thought that the fundamental particles in nature were protons, neutrons, and electrons, basically. And then they discovered photon, light. And then they kept digging deeper and deeper and deeper. And by now we have a much more elaborate theory in which electrons are still fundamental particles and photons are still fundamental particles. But protons and neutrons we now know are not. We know that they're made of smaller pieces called quarks. They're each made of 3 quarks. So quarks are particles that are discussed in the Standard Model. And then another thing they discovered is that when, like if you just have a neutron sitting by itself, which doesn't happen too much on Earth in nature, but if you do, it will actually decay. It will actually turn into a proton and an electron. But it also, they eventually discovered, shoots out another invisible sort of particle, very hard to detect particle, called a neutrino, or it's actually an anti-neutrino. And so in addition to the electrons and the various types of quarks, neutrinos are also particles in the Standard Model. So it tries to explain those particles. I mean, it tries to say what they are, so try to say what the properties are, and it tries to say how they interact with each other. And it does a really remarkable job at terrestrial scales, not counting cosmic observations, some of which are very mysterious. But at terrestrial scales, it seems to do a damn good job of explaining sort of all the physics we know.
Okay.
So there's like you could do it historically, like you could work your way into it, starting from the protons and neutrons. A mathematician might want to just like see what it is right away. But there probably are some aspects of it that are easiest to understand from a historical point of view, because otherwise it's just like slapping a bunch of rather strange stuff on the table without any warning. So in our paper, we took a kind of pseudo-historical point of view where we weren't trying to, actual history is always much more complicated than the pseudo-history that mathematicians and physicists like. But a sort of pseudo-history leads you into the standard model for some kind of logical development. So we tried that.
So we give a little context just to give a little more shape before we just dive right in, right? So we're going to talk about the standard model, right? And it's the standard model of particle physics. And, well, in physics, we have four fundamental forces, right? We have gravitation, electromagnetism, the strong, and the weak. And famously, the standard model is going to, well, only encompass these three, but it leaves out gravitation. And of course, one of the holy grails of physics is to have a quantum theory of gravity, and therefore incorporating gravitation into the standard model. That's a whole another subject that we're not going to get into. We're going to focus on the standard model as it is, and maybe some extensions of it, but not talking about gravity. But since we have these three forces, it turns out that the type of symmetry group we need to consider, what physicists would call a gauge group, right? Right. That's going to be SU3 cross SU2 cross U1, and we'll explain this more in a bit. So these are all basically what are called Lie groups, right? So there's a Lie group is basically a group that's continuous. You can think of it as basically matrix groups. These are all just groups of matrices, and these matrices tell you how particles transform among themselves, right? And so I guess so. First of all, that's basically the standard model in a very quick nutshell. You have particles. Particles interact in various ways through forces, and the symmetry groups that mediate all these elements consist of this SU3 cross SU2 cross U1, and it looks maybe a bit funny or baroque at first, but that's precisely what we're going to get into. There are extensions or ways you can repackage the standard model, right? So there are so-called grand unified theories, or GUTS for short. And there you can try to look at a larger structure which might also explain the standard model in a consistent way. And of course, because you've done something different, there are other consequences you might have to check. We're going to go into one such, the mathematics behind one such extension known as the SU5. But there are two other famous ones which you go into your paper. We might only say brief remarks about them, but I'll just write them here just to be consistent. There's also the SO10, which is really spin 10, but I think it's called SO10. And then there's the so-called Pati-Salam model, which has its own group, SU2 cross SU4, if I'm not mistaken, correct?
It's SU2 times SU2 times SU4.
That's right. I forgot the other one. Yeah.
Okay. So that one, you'll notice, looks more complicated. So some people argue that one's not really a grand unified theory because it still has these different pieces in it. But it is a bigger, more complex, bigger theory that's trying to explain some mysteries of the standard model.
That's right. Okay, so now that we've at least fleshed out some of the technical aspects, so I think the route we're going to take, I guess, following your paper, is that we're going to sort of motivate how. So let's back up a bit. So uh, in the early and middle part of the 20th century, physicists were discovering all kinds of particles, and they were trying to find ways to make sense of all that mess, basically. And I guess one of the first observations was that somehow you can treat the hypothesis was that you could treat a proton and a neutron in a unified manner, that maybe one could be transformed into another, right? So I think that was maybe one of the beginning stories of how to use gauge theory in say nuclear physics. So I guess you're going to start with that as a historical motivating point, and then we're going to dive into the particulars of the standard model. Is that correct?
That's yeah. There are lots of ways to get into this story, but that's a perfectly fine one. So people had noticed that the atomic nucleus is made up of two kinds of particles, protons and neutrons, and they're mysteriously similar. They don't have the exact same mass, but they're very close masses. So like the proton is 1,836 times the mass of the electron, and the neutron's just like a tiny bit more heavy than that, which is weird, right? They have these like two particles that are gigantic compared to the electron, but like almost the same mass, but not quite. The proton is positively charged. The neutron, as you might expect, is electrically neutral, so it has charge 0. So they're very dramatically different in terms of electric charge. But in terms of some other forces, the nuclear force that makes them actually stick together from a nucleus, which is required because if the electric force was the only thing around, the protons would all repel, and there's nothing negatively charged in there, so they would just shoot apart. So they knew there had to be some force keeping them together. And they studied that, and they discovered with respect to the nuclear force, which is what we now call the strong nuclear force, they act identical. Let's say act identical. So it's a really interesting mystery there, sort of the same in some way, different in other ways. And so Werner Heisenberg came up with this theory that said, in its very simplest form, it says that like the proton and the neutron are actually the same particle if you ignore the electromagnetic force. So you have to sort of like make believe and say, forget their electric charge. They're the same as far as nuclear force goes. But there are two different states of the same particle, two different ways that particle can be. And then people had developed some math already for dealing with such situations. People had developed the mathematics of what's called spin. And for example, if you have an electron, it actually acts like a little spinning thing, a little spinning dot, but it's a very quantum mechanical spinning thing. So it's very peculiar compared to like a spinning baseball. In particular, if you measure its spin along some particular axis, you always find that it's either spinning up, that is, it's spinning like clockwise with respect to that axis, or spinning the other way, counterclockwise. Never anything in between, just always one or the other. And that's really bizarre because that's true no matter what axis you measure it along, you always see that. So that's a completely paradoxical from the point of view of classical mechanics. But people figured it out, first for the electron, and then when I could get into arbitrary amounts of detail about that, but then that was well known by the time Heisenberg was trying to do his thing. So what he said is, hey, maybe there's like something else that's like spin, and he called it isospin. Because there are like different isotopes of atoms, so it doesn't matter that much why it's called that. But it's like spin, but it's not. So he made up a thing called isospin, and he said that the proton and the neutron were the isospin up and isospin down states of a single particle, which he called the nucleon.
So let's actually unpack that a bit, since we've spoken for quite a while. So let's backtrack. So we have protons and neutrons. These are two massive particles, as you pointed out. We also have electrons, and electrons have something called spin. Well, I guess they they technically all have spin, but let's just particularly an electron has spin. Now, one interesting, well, spin's kind of a funny word because when we talk about electron having spin, it's not literally what you just described in terms of like a tabletop, with this rotation, but what it actually is the following. Basically, let's back up a bit. So we have a group called SU2. Maybe we should finally define what that is. So we have this group, SU2, and you can think of it as the group of all 2x2 complex matrices that can be, I guess, written as the following. So you're going to have it be, I think that
the minus sign there on that beta bar.
Yeah, that's right. Yeah, I was hesitating for a second there. Right, where the norm squared and the sum of the alpha and beta are going to be 1, right? So here alpha and beta are complex numbers. Right. So you can think of SU2 as 2x2 matrices that can be parameterized by alpha and beta as such. You can also describe it in terms, just saying a few words. Basically, you need to be, so it's 2x2 matrices. It needs to have, it needs to be unitary, meaning that the columns form an orthonormal basis. You're using the Hermitian inner product on C2, and then you also finally need determinant 1, which is how you can work your way to that formula. Basically, I was putting bars and minus signs such that the determinant 1 is satisfied once you have that constraint on the norm of alpha and beta.
Yeah, I can imagine people who think that the first description is much more complicated, and I can think of people who say the second one is much more complicated.
Sure. Depends on whether you're symbolic or verbal. I don't know, but I think it's good to have both.
Definitely, it's good to have both.
Yeah, exactly. So, anyways, the point is that SU2 being a group of 2x2 matrices, it acts on the vector space C2. So this acts on C2. It just means that given an element of SU2, I know how to multiply it against a vector in C2, which is the usual multiplication, right? If I have a 2x2 matrix and I have a vector in C2, I just multiply a matrix and a vector in the usual way, right? So just explicitly, if I have a G in SU2 and a V in C2, then I can form G dot V, which is also in C2. Just the usual matrix multiplication. Okay, and what spin up and spin down, what they mean is that there's a basis for C2, and one basis vector is the up basis vector, and one basis vector is the down basis vector. So you can think of, let's just write this. You could think of a span of, let's just say, okay, 1, 0, 0, 1, and we could say this is the up direction, and that's the down direction, right? So that's the mathematical sense in which we have spin. And basically, now what we're saying is that, well, protons and neutrons. So now let's go back to your thing about isospin, right? So why is it like spin but not quite spin? And we gave it a different name. Well, so spin involves 2 degrees of freedom, up and down. Protons and neutrons you could also think of as 2 degrees of freedom by virtue of the fact that there are 2 particles. And if you think of those 2 particles as spanning a 2-dimensional vector space, they could have other degrees of freedom too, but we're just specifically focusing on the proton and neutron themselves as two states. Though by analogy, we could also think of there being an SU2, a different SU2, not spin SU2, but isospin SU2 that transforms proton and neutron between each other, right? So there's like a proton basis vector, a neutron basis vector, and then there's an SU2 that acts on both. Well, there's always a convention about what's up and what's down. I guess they're somewhat arbitrary because there's really no universal up or down. I mean, I guess there is a notion of what is right and left, but maybe we don't have time to get into that. But at least for now, up and down are a bit arbitrary. But by convention, proton is going to be the up direction for isospin, and neutron is going to be the down direction for isospin. Is that correct?
Yeah, that was just an arbitrary decision in a way. I guess one reason why it's mildly memorable is, I don't know if it is memorable, but people are used to it by now, is that protons have charge 1. They're positively charged, and we say their charge is 1. And neutrons have electric charge 0. And this is like the beginning of something that of a pattern that people regularly see. And so it's, as you say, it's to some extent an arbitrary convention, but we say like the up things have more charge than the down things. So it's just easy to remember anyway.
That makes sense. Okay, so just to explain a bit of spin very, very quickly. So spin ultimately has its origins in rotations. So we're in 4 dimensions here. So there's the 4-dimensional rotation group SO4. So you can think of this as the group of 4-dimensional rotations, or if we want to think about it in terms of a more precise algebraic description, it's the set of matrices in, let's say, 4x4 real matrices, such that A transpose A is the identity matrix. Okay, so basically all the columns are the columns form an orthonormal basis. So that's what SO4 is. Now, and by the way, let's just worry about Euclidean signature. It's not going to really make a big difference. Okay, so there's this group, and how does spin enter into it? Well, for somewhat technical reasons, we want to work with something that's not quite SO4, but it's more simple topologically. It's what's called simply connected. There's a group called spin 4, right, which is a bit bigger than SO4 in the following sense. It's what's called a double cover of SO4. So double cover just means there's a 2-to-1 map with some nice properties. Just to give an analogy of what a 2-to-1 map looks like, for example, you can have, say, the 2-sphere inside R3, and then you also have the set of lines through the origin. Okay, the set of lines through the origin R3. This also has another name. This is called RP2, the real projective plane. And there is a straightforward 2-to-1 map from S2 to RP2, right? So this is also a double cover. What is that? Well, here's this 2 sphere that I just drew, and then there's all these lines that go through the origin, and each line is going to intersect the sphere twice, right? One at some point x, and then one at its corresponding antipodal point minus x, right? So each point on the sphere maps to a unique line through the origin, and there are 2 points corresponding to every line, right? So that's an example of a 2-to-1 map, and spin 4 is basically the analog of that, except that instead of mapping into RP2, you map into SO4. Okay, so that's what a double cover is. Now this looks a bit strange, but this is sort of what you have to do in order to define spin for topological reasons. So once you accept that there's a group called spin 4, which is the double cover of SO4, the next fact that you need to know is that it turns out somewhat, I guess, I don't know if miraculously is the right word, but it is a fact that spin 4 turns out to be the group SU2 cross SU2, right? So 2 copies of SU2. We already defined what SU2 is, but you get 2 copies of SU2. And this is how you define left and right, because we define the spin of a particle to be spin is basically going to be a representation of spin 4. Well, what are the representations of spin 4? Well, it's going to be C2 direct sum with C2, because there's 1 copy of each SU2, and 1 copy is the left and 1 copy is the right. Okay, so let's say left and right. So here's left and right. So long story short, when we talk about particles having spin, right, in general, if there's both left and right involved, you're going to have a 4-dimensional vector, this 4-dimensional degrees of freedom that it has. If you talk about left or right, then you restrict to either the left part or the right part, one of these factors of C2, and that basically goes along for the ride. So in other words, later when we talk about the standard model, we're going to have all these particles, quarks, neutrinos, and whatnot, and the notation won't be explicit, but in the background, there's always this C4 or this C2, depending on whether you're talking about all the spins or just one of the spins. That's always floating around in the background. So the mathematical terminology would be that you're always tensoring with some representation of spin in the background, basically.
One thing I'd like to add is that I will be referring to right-handed and left-handed particles quite a lot. So this was useful. So I think what I want to start doing at some point, maybe soon, is start making a kind of list of the matter particles or fermions in the standard model and sort of slowly go through it and talk about some of their properties. But one of the properties is that each one of them is going to either be right-handed or left-handed. So so that's what I'd like to get into at some point.
Yeah, we're jumping all over the place, but I think it's it's fine. One of the fascinating things about physics, particle physics, is that there's a parity symmetry violation in the sense that, as we'll see, the weak force only interacts with left-handed particles, not with right-handed particles. So nature does make a distinction between left and right. And at the level of mathematics, it means that the particles that have this representation tensored with them interact with the weak force, but the other ones on this right one do not. So that's the main thing to keep in mind. And so
we'll definitely be seeing that a huge amount, and part of the math of what you just said is that the left-handed ones will come in pairs called isospin up and isospin down, because it turns out that this isospin, which was first introduced by Heisenberg for sort of practical reasons, is actually crucially related to the weak force, the force that does things like causes nuclear decay, and so those guys that come in isospin up and isospin down pairs, they will interact with the weak force, and they're the left-handed ones. But then we'll also see a bunch of right-handed particles, and those will transform in a different way under this isospin SU2. Namely, they will transform in a one-dimensional representation of SU2, where SU2 doesn't do anything at all to them, so that it's called the trivial representation of SU2. And so there's this dramatic difference in behavior between the left-handed particles and the right-handed particles.
But just to clarify, while we have all this stuff here, so what you just referred to, so let's do a little review here. So we said that the gauge group of the standard model was SU3, SU2, U1. What you just referred to in terms of isospin, it's a little confusing because, as you also point in your paper, there's sort of this SU2 is corresponding to the weak force, and there's so weak isospin, but this is different from the isospin we talked about earlier with nucleons. But
I'll say that it's only slightly different, and there's actually a correlation between the two, so it's not worth worrying about.
That's right. Yeah. But okay. But some people will call it weak, but for our purposes, we'll just call it isospin for thereafter. Yeah. Well, just so people aren't confused with the proton-neutron story. But anyways, so the isospin always refers to some SU2 that's not corresponding to the rotational spin. That's what isospin always means. But this SU2 can act in different ways. And what John, you just said, is that SU2 acts in the standard representation for the left copy. So this is now the standard representation. And this is the trivial representation for the right-handed copy, where trivial means that it doesn't do anything. Every element acts as the identity for right-handed particles.
Yeah.
Great. Okay, so that. I think it was worth, going into this excursion about spin, just so we have something a little bit more concrete with which to understand what these groups are doing. So, John, did you want to maybe now
Yeah.
go into the zoology of the standard model, essentially.
So let me try to start out with more familiar particles, and then maybe talk about some less familiar particles. So electrons are called by physicists E minus because they're negatively charged, and because we will have to get into it, they have an antiparticle, which is called a positron. It's like the antiparticle of an electron, and it's positively charged. But we'll get to that when we do. But as I've already suggested, we've already discussed, there's going to be like a left-handed electron. Then also there's like a right-handed electron. And they are very different in the following sense that, I mean, they don't look different electrically, but they look very different with respect to the weak force. And because the right-handed one transforms trivially under isospin SU2, whereas this one is transforming non-trivially, but it transforms in an interesting way because so this would be like this is like one basis vector of a two-dimensional basis of a two-dimensional vector space, which is the one that Tim was just drawing. But what's the other basis vector? Well, the other basis vector is actually for a neutrino. It's for a particle called the electron neutrino. So these two together are lumped together in the standard model as an isospin up and an isospin down state or basis vector in a certain two-dimensional vector space. Now, which one is isospin up and which one is isospin down? Well, I wasn't so organized as to make the one on top be the one that's the isospin up. It's good to stick to a convention where the electric charge is bigger for the isospin up one. So Q, for some mysterious reason, means charge in physics. So the neutrino is an electrically neutral particle, so it has charge 0, whereas the electron is a negatively charged particle, so it has charge -1. So we see here that the one with the bigger electric charge is the neutrino. So this would be the one we would call isospin up, and this is the one we call isospin down. Now there's
just like with the proton had +1, which is a charge which is greater than the neutron. So it had its isospin being up and the neutron being down. It's exactly similar.
Yeah, so we're going to keep seeing that type of pattern over and over again for these pairs that are two basis vectors in the copy of C2 that is a representation of isospin. This guy is sort of all by its lonesome. It's not, well, it's transforming trivially under isospin, but it still has electric charge -1, just like any other electron. And then you might say, okay, that's the left-handed E- and neutrino. Here's the right-handed E-. What about the right-handed neutrino? Yeah, so no one knows if right-handed neutrinos exist. They haven't been detected, but they're also would be very elusive if they did exist, because they're, well, what is it? For it to even be a neutrino, we would say that its electric charge was 0. So I'm going to write a 0 there, even though this is a particle we haven't seen. And the pattern that we observe elsewhere is that the right-handed particles are transformed in a trivial way under SU2. So it would not be feeling the weak force either. And I haven't even gotten to the strong force, but it wouldn't be feeling the strong force either. So it just would not interact in any way if it existed and fit the pattern as in the simplest way you'd expect. So that's why we're not shocked that we haven't seen it. It might exist and be very hard to detect. So I'm going to put it in there because it's going to come in handy to have it there.
Actually, two questions really quick while we're lingering on this. One, you mentioned this thing about charge. Does it have to have charge zero, or is that speculation?
It's speculation. If it didn't have charge zero, it 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 wouldn't it wouldn't be a neutrino of the sort of any sort that we've seen. So it so you could say it's a speculation. We could discover some light
Sure.
particle that was like a neutrino but had charge 3 or 1, and we'd be all very excited and shocked.
And then the other question is, so the way you've phrased it with this right-handed stuff, you could ask the same thing about, like, what's special about being right-handed? Because we know we have right-handed electrons, and I think the answer is that, electrons have mass, and so in the for those who know more, right, if you have a massive Dirac operator, so the Dirac operator is what occurs in the standard model, then the left-handed and right-handed particles are going to interact. But I guess I think the point is that since neutrinos are believed to not have mass, then you could have this right-handed particle doing its own thing, essentially. But I think there's now some conjecture that they might have mass, so wouldn't that make it easier to detect the right-handed neutrino?
Yeah, that's correct. At least some neutrinos we believe need to have mass to fit the experiments we have. There could be one massless one, but I think we know that there have to be two massive ones. I've only talked about one so far, so it's not quite clear what I'm talking about yet. But anyway, so there could be like indirect ways that we would detect this right-handed neutrino if it existed. People are busy doing experiments with neutrinos to try to get to the bottom of such questions, but they're very difficult experiments to do. So it's the jury is still out on that, I'd say.
Is that like if you were to rank it alongside, like, say, so the LHC was built, I guess one of the main reasons it was built was to discover the Higgs boson, and it was, of course, a huge success that it was discovered. Is that also the same scale at which people are going to try to detect neutrinos, or is that just completely different territory?
Well, you use a completely different technology to detect them. You don't build enormous particle accelerators. So even the biggest neutrino detectors are much cheaper than the LHC. But what you basically do is you build enormous tanks of things like liquid argon or other substances that are transparent, that if a neutrino interacted with it, it would make like a flicker of light. And people either let neutrinos from the sun and other sources be detected by those tanks, or actually create particle beams by smashing particles against each other, including at the LHC, and then try to detect neutrinos that have shot off by means of these tanks. And it's not as expensive, but it's still a big deal in particle physics. Yeah, so this is like low energy particle physics. In the particle accelerators, you're trying to make super heavy particles, but neutrinos are super light. But you still need really extensive equipment to catch them, because they interact only with a weak force at most, and this kind would be like interacting like only, not even with that, only detectable through changes in behavior of other neutrinos that do interact with the weak force. So yeah, it's a really interesting story.
Okay, great.
So I'm gonna march on, and I'm gonna bring in the quarks. And so the deal with the quarks, let me just sort of motivate why we started believing in quarks just a tiny bit. So I said that like the proton and the neutron are now known to not be fundamental particles. They consist of more basic constituents. And without getting into too much detail about how we do know that, they're both made of 3 particles. And it's known now that the proton is made of 2 quarks called up quarks and one called a down quark, whereas the neutron is made of 1 up quark and 2 down quarks. So I'm not going to try to prove to people that has to be the case. But if you believe this, you can see a bunch of things already. Namely, for example, so the proton has charge equal 1. The neutron is neutral, it has charge 0. So you can just figure out what the charges of these U's and D's would have to be to make their charges add up to the correct numbers. So that's a little bit of algebra. Well, let's not shirk a little algebra, I guess. It's like this is like the easiest piece of math in the whole story here. So we know that 2U plus D is 1, but U plus 2D has got to be 0. The result of this algebra was pretty interesting. Did I say that right? Yeah, I said that right. So if I want to like cancel one of them out or something. Well, let's see. One thing we can do that's just very tempting is to subtract the bottom equation from the top equation. So that doesn't like solve for any one of them, but it says something pretty interesting. So it says U minus D equals 1. So the charge of the up quark has to be 1 more than the charge of the down quark. Now, you may have noticed I've repeatedly said that like when you have these isospin up and isospin down pairs, the one with the bigger charge we call up. And so this is fitting into this pattern, and that's sort of why it's called up. But what are these numbers? Well, I guess I'm trying to find, let's see, I'm trying to like avoid doing the algebra in some brutal manner, try to do it in some fun manner. But one thing you can see right away is that it's not going to work to have the U and D be integers. And this was like a huge shock because until quarks came along, people thought all particles had integer charge. But I guess what we could do, maybe I could just do this. I feel like adding the top and the bottom equation, and we see that like 3 times the up charge plus 3 times the down charge has got to be 1. That's so what's the best? Why don't I give it over to you? What's the best way to what's the like, I mean, I could solve it, but what's like the nicest way to solve it?
The way I would have done it is I just take a linear combination such that one of the variables is eliminated, right?
Yeah, so, but that's like so gross. Yeah, I know. Of course I know how to do that, but okay, what the hell? So like I'll multiply this. I say I want to figure out what the charge of the up quark is. So I'll like multiply this top equation by 2. So I'll get like, sorry, and I'll do it in this disgusting way, 4U plus 2D equals 2. And then I'll like subtract this bottom one from this top one. And so then I get 3U, and these cancel, equals 2. That wasn't too terrible, I guess. Yeah, it just seems like unmotivated to me physically, but okay. So we're seeing that U is 2/3, which is, and then D is 1 less than that. So D has got to be 1/3. So we're, and this has actually been like shown experimentally. Sorry, D has got to be, did I say it correctly? D has got to be -1/3. And then you can just check that like 2/3 plus 2/3 minus 1/3 works. It's 1, and then 2/3 minus 1/3 minus 1/3 is 0. So we're getting these interesting charges for the up and down quarks. That really came as like a big shock to people because they had never known about fractional charges before then. There's more to say about that, but let me just start getting them onto the picture here. So I'm going to have my U and D, and and it turns out it works like the other ones in the sense that like there's 2 that are sort of joined at the hip, which are the left ones, and then there are 2 that are the right-handed ones that do not feel the weak force, and they're like separate from each other. And so we know the charges of them now. There's like 2/3 and -1/3, and the charge doesn't care about all this left-right baloney.
Yeah, just to remind people, as I said earlier, when you see right and left, there's secretly a copy of C2 living being carried around. So it's just tensored with everything else that's going on. So these particles might, as we'll see later, some of them might have other degrees of freedom, but what's being suppressed here is the C2 that's coming from the left and the right.
Yeah, it's sort of lurking in the background.
Yep.
So these are the particles of what's called the first generation of the Standard Model. They were the first to be discovered, but what's interesting is that later on people discovered more particles called the second and the third generation, but I'm not going to talk about them a whole lot. And the reason why is because they are like carbon copies of what I've just written down here, except that they're much heavier. They're heavier for the second generation. They're even heavier for the third generation. So like in addition to the electron, there's a particle has all the same data that I will be writing down here called a muon, which is like 207 times heavier than the electron. And when it was discovered, a physicist said, who ordered that? Because there's like no reason they knew why it should exist. And in fact, there's still no reason known why it should exist. And then there's like an even heavier one called the tau particle. And then it was later discovered that each one of those has its own neutrino. And it was discovered that that in addition to these quarks, there are quarks in the second generation and quarks in the third generation. But for all the data that I'm going to be writing down, which is not including the masses of these particles, for example, they will have the exact same data as what I've written down here. So I'm not going to talk about them. I'm going to talk about just the fermions in one generation. So there's a lot more complexity, which I'm suppressing here.
Sure. Yeah, sorry,
which involves the Higgs boson.
So when we wrote down the gauge group SU3, SU2 cross U1, that neglected the Higgs boson. At the level of the gauge group, these generations don't interact, right? Because the representation split into three copies of that. But is it only to the Higgs boson that actually the three generations interact from this term in the Lagrangian?
Yeah, that's right. So if you can imagine, so you could imagine it this way, that like I'm imagining telling you a story where I've like eliminated the Higgs boson. And if I eliminate the Higgs boson, what would happen would be that actually that all these particles would be massless and the three generations would not interact with each other at all. And so that's like a simpler story to tell, which we'll already see like plenty of complexity and enough to keep us happy for a couple of hours.
Sure. Okay. Anyways, okay.
But it's good to admit. It's important to admit that this is like being sloughed over. Huh?
Yeah. I think it's good to always know what's being skirted over. So anyways, please continue. What's next?
Well, I'll just briefly say that actually each of these quarks comes in like three kinds called red, green, and blue, quite arbitrarily. And that has a lot to do with this SU3 group that you mentioned, which is connected to the strong force. So that will enter at some point. But I think what I mainly want to do right now is continue on with this little story about the weak force and isospin. And so the name that people use for isospin is I3. It's like this isospin in the third axis, like the Z axis, if we were thinking physically. But let me just indicate what that is. So a bunch of these guys are coming in pairs. The left ones are coming in pairs, where one of them is isospin up and the other one is isospin down. And it's just a habit of physicists to use, for up, they use 1/2 as the value of isospin, and for down, -1/2. If mathematicians had been in charge from the very start, they may have used 1 and -1 here. But there are good, not completely stupid reasons to use these values. So I'll do that. I don't want to deviate from tradition there. These guys have no isospin. so that they're not interacting with the weak force. These guys are coming in pairs, but here this one has the bigger charge, so it has the bigger isospin, so it's like 1/2 and -1/2. And then this is 1/2. And this is -1/2. Wait, sorry, I'm sorry. Those guys, sorry, that's not true. These guys, the right-handed ones, have no isospin. They're not interacting with the weak force, so they have no isospin. So the guys that go like 1/2 and -1/2, these ones that sort of are coming in pairs, or physicists will sometimes call them doublets. That should be reminding you of the stuff that I was saying about how we have this isospin up vector in C2 and this isospin down vector in C2. Actually, Tim was saying this. And so so physics jargon is that like this one has I3 equals 1/2. It's just
right. So another way of saying this in representation theoretic language, you have a representation of SU2 and therefore a representation of its Lie algebra, which would be traceless skew Hermitian matrices. I3 is a generator, and you look at these up and down or basis vectors, and then you look at the eigenvalues of the I3 operator in that basis, and then this is just saying that in the two-dimensional representation, the way we've normalized things is such that I3 will have eigenvalue +1/2 for the 1,0 vector, -1/2 for the 0,1, and then in the trivial representation, well, it's I3 maps to the 0 vector like everything else, and so yeah, you only get 0 isospin.
Yeah, that's right. So you can make up a 2x2 matrix, which might also be called I3, but I put a hat on it because it's not these numbers. And this matrix, when you apply it to this vector, it multiplies it by 1/2. So that's an eigenvector. And then when you apply it to this vector, you multiply it by -1/2. So that's also an eigenvector. And then their eigenvalues are these numbers here, which perhaps confusingly are also called I3, but
Sure. Yeah, this is where physicists are sloppy, where they confuse operators with eigenvalues, and then there's also this thing about multiplying by I and -I because the Lie algebra actually is skew Hermitian, but if you want real valued eigenvalues, then you need to also divide by I essentially. So anyways, those are details we're all sweeping under the rug. But at the end of the day, you have eigenvalues when you normalize things so that they're real, and in this case a half integer, then this is what you're going to get.
Yeah, so that's a little bit more of a story about what's going on in this column of the chart. Now, what people did at some point was they decided to look at the difference of the charge minus I3, because they've noticed there's this kind of correlation that things that have bigger I3 have bigger charge. The isospin up things have bigger charge than isospin down things. And so it's very natural to think about, like, why isn't the charge just the same as I3, right? Well, they're not the same, but they both get bigger sort of hand in hand. So it's very natural to like ponder the difference between them. And so this winds up turning out to be like a very important quantity in physics. So we can just work it out. So we see that like here, the charge is, I guess, 1/2 less than the I3. This is also 1/2 less. This is 1 less. This is the same. These get a little hairier. So 2/3 minus 1/2 is a 1/6. This is also a 1/6. this is 2/3, and this is -1/3. Now this looks pretty hairy, right? I mean, it doesn't look like there's much of a pattern here. But the only pattern is that the fellows that are isospin doublets, the ones that are like in the same, the ones that I'm putting brackets around, they will have to have the same value of this quantity because because they don't have to, but we've noticed that like when the isospin goes up 1, the charge also goes up 1 in these cases.
Yeah. So. Just one thing you said, which I was thinking in the background while you were doing this, but I think I know the answer now. You were saying, oh, why is this relationship between charge and isospin? On the one hand, you said earlier that the convention was to have the higher isospin correspond to the higher charge. So in some sense, you define it that way. But I think what's the real mystery, though, is that you can, because I3 is shared among all the particles, you could set that arbitrarily, which particle gets the higher I3 for one of these doublets. But then because I3 is shared among all the particles, then you're sort of stuck with that elsewhere. So there is a constraint. You can't independently choose the higher I3 for all these guys. There actually is a constraint. So that's the answer to why I was a little bit confused when you first said, why is there this relationship between Q and I3? When at first you said, oh, we just kind of made a convention. But of course, the answer, as I just said, is that because you're sharing the I3.
Yeah.
Yeah.
That's right. Yeah.
Okay. Yeah.
So now some quantity along the lines of this, it's actually some quantity proportional to this, got the name hypercharge. Because it's like connected to charge, but it's like more mysterious. Now, charge. Well, okay. So what about plain old charge? So charge. Before quarks got onto the scene, we thought we understood charge. Charge was an integer, and back in those days, the way we would say it is that charge is coming from representations of the group U1. So we didn't talk too much about this group yet. This is like the simplest of these various groups we've been talking about. This is just a group of 1-by-1 unitary matrices, or if you prefer, and most people probably do, just like all the numbers e to the I theta, where it's like theta is a real number, or it's, in other words, unit complex numbers. I mean, there are like tons of ways to say it, but it's the unit circle in the complex plane. And if you take two numbers in the unit circle and you multiply them, it stays in the unit circle. And this is a very nice group. It's abelian, unlike the other ones we've been talking about. And it has a lot of representations. It has a lot of different representations on just that are one-dimensional, so that you can think of them as representations on the complex numbers. It has different representations. Let me call them like representations rho sub n, where n is some integer. So it has one representation on C for each integer. And the way it works is that you take your unit complex number and you want to let it act by this operation on some vector, but this is just a vector in the complex numbers. And the way it works is you just multiply by z to the n. Multiply that vector by z to the n. So in other words, you can just multiply by z, and that's called a particle of, I should say it. This n winds up being called the charge of the representation. And so if you have a particle of charge 1, in the old days, what we would say is that it's a particle in which this symmetry of U1, just a kind of rotation, circular type of symmetry. I mean, when I'm writing this stuff, you're supposed to be having this kind of little picture in your mind. That's what U1 looks like. That kind of way of turning a particle around can act on your particle. And if you just multiply by the complex number itself, you call it a particle of charge 1. If you multiply by Z inverse, it's called a particle of charge -1. If you don't do anything, n equals 0, you're not multiplying by 1, you're not doing anything. That's called a particle of charge 0.
Right. And maybe to make it a little more intuitive, when you raise to the nth power, it becomes e to the I n theta. And you could think of that n as essentially a coupling constant, right? So it's saying that the coupling of this theta, this Lie algebra generator is n times stronger. And that's, you can think of that as a measure of charge as well.
Yeah, we haven't really gotten into enough to say too much about that, but that's a good way to get started. So the fact that this is has a more dramatic effect when n is bigger winds up meaning that particles with bigger electric charge get more strongly affected by the electromagnetic force through a long chain of reasoning.
Sure, right, yeah.
But that's definitely right. So now when people discovered particle, so this looks like a wonderful story, and this story, if you're a mathematician, might easily convince you that it was impossible to have particles of fractional charge. And the fact that nobody had seen any particles of fractional charge made it all the more plausible until quarks were discovered and had these fractional charges that we've discovered. So how in the world do you get out of that mess? Well, it turns out that first of all, one way you could have gotten out of that mess that's fairly, sorry, I'm looking for where I was here. One way that you could get out of that mess is you could, which is oversimplified, but it gives you an idea of how we can escape this kind of dilemma, is you could say oh, we're suddenly discovering a particle of charge 2/3, or let's say -1/3. Well, actually, we just were wrong all the time about when we said a particle had charge 1. Those things that we thought were charge 1, they actually had charge 3. So so we just hadn't ever found a particle of any smaller charge, so we called it charge 1, but we were we didn't know what was going on. And so when you see a particle of charge -1/3, then you should say oh, we should just redo our math and get things straight. And now we'll say that particle has charge -1, assuming, of course, we don't discover any more particles with even smaller charge. So that's certainly possible to do, and that's basically what people were forced to do when they discovered that particles can have fractional charge.
I see. So actually, I was going to say, in terms of fraction, if you want in mathematical terms, if you want a representation of the Lie group, which is stronger than a representation of the Lie algebra, then you need this integrality condition in order for the representation to make sense at the level of Lie groups. And you're saying that from that perspective, that you can't put a 1/3 there because you wouldn't have a representation. But I guess there is some actual pre-multiplier constant that sort of that maps things such that really, in other words, the circle is 3 times bigger than you thought it was, right? So it's really 3n. Is that basically what you're saying?
Yeah, that's basically right. So you could say you thought you knew what the physically relevant circle group was, but actually the really important circle group is this one here that has a 3-to-1 cover. And so
okay.
And so so that what you thought you were turning something around once down here, in the new picture it's going around 3 times. And so you thought an electron had charge, well, a proton had charge 1, but in this new story, this new mathematical story, it has charge 3.
Yeah.
So it's actually not unlike this double cover stuff that you were talking about. You can get symmetry groups wrong or slightly wrong, and then say, whoops, I should have been using some other group that was a covering group of that.
Sure.
But the particular, especially weird thing about the circle, as opposed to something like the SO3 that you mentioned, is that you can keep on doing this arbitrarily. You can keep on changing your mind and saying like, oh, I want to use a cover of that because it has the universal cover, as it's called, is the whole real line. And you can wrap that in lots of different ways around the circle, roughly speaking.
Yeah.
So, yeah.
Yeah. I was going to say also, I don't know if this might maybe just say a few words about it, but one of the famous properties of quarks is they're not observed in isolation. So I'm wondering to what extent quarks were discovered. What does that even mean? Nevertheless, because of the way they mathematically occur in the standard model, you know that they still have to have a well-defined representation. So that sort of necessitates this story. But in terms of discovering them or that they exist, so to speak, can you just say maybe a little bit about that?
Yeah, well, for a long time, people were suspicious of quarks for all sorts of obvious reasons. One being that we didn't actually directly see them. Our theories of the nucleus worked very well if we assumed that protons and neutrons were made of quarks. But by now, we're actually getting better at doing experiments. So, for example, now we are able to do collisions of atomic nuclei at such high energies that for a short while they become so hot and they collide so energetically that the quarks freely roam around in a little blob of stuff called a quark gluon plasma. And so it's true that it's like after much less than a microsecond, that blob cools down and then it turns protons and neutrons, and there are reasons we know why you're never left with a lone quark when it's done, but we can actually do experiments that under these extreme conditions, quarks act as if they are able to, they can freely roam around under these extremely hot conditions. And there are others, not quite so intense experiments where you can shoot an electron and a proton and see that it's bouncing off of components inside the proton, and it's bouncing off as if those components have charges 2/3 and -1/3. You can by how strongly it interacts with them. So it's not just a metaphysical sort of thing that you can never really see. It's hard to see the quarks, but you can there's definitely tons of evidence that they're there and that they have these charges. Yeah.
Okay, great.
So here I was telling this story to say, like, first of all, you might think charges had to be integers, but then if it turned out you get things of charge like 1/3 or 2/3, you could just change your conventions and say, oh, what we thought was charge 1/3, we're going to call that charge 1 now, and everything will work out. You just multiply your definition of charge by that integer. And so that's basically what goes on here, except it turns out that the really good context in which to do that is not for charge, but this thing, this is called the hypercharge. So it turns out that in the standard model, we've mentioned this group SU3 times SU2 times U1. And we've talked the most about the SU2, interestingly, which is this isospin for the weak force, this isospin SU2. We haven't talked at all about this SU3 yet, and I'm starting to talk about U1, and I sort of said, oh, U1 can be used as a theory of charge, but actually in the standard model, this U1 here is not for charge, it's for this other quantity called hypercharge, which is connected to charge, but it's not the same as charge. And this U1 here is connected to this thing here. However, you'll notice these things aren't integers. These numbers here aren't integers. So what I'm going to do is I'm going to not work with this quantity. I'm going to work with 6 times this quantity, which will be enough to, multiplying it by that is enough to get all these guys to be integers. Now, I'll just mention that historically, people were not quite smart enough to multiply it by 6 and call that the hypercharge. For some weird reason, they multiplied it by 2 and called that the hypercharge. And so they still were left with some fractions running around. But the whole story is clearer and more logical if you work with hypercharge being an integer. So y is, for some reason, the typical symbol for hypercharge. And I'm just putting this tilde over it to reassure experts that I actually know what I'm doing here, that I'm not doing the usual way of doing things. I'm doing like the way that they should have been done, which is to multiply it by 6. So I'll start calling this thing hypercharge, even though it's like off by a factor of 3 compared to standard conventions. But this is enough to make it an integer. So we get these hypercharges. And they're still weird, of course, right? So let's see what they are. -3, you catch me if I screw up, okay? I'm just multiplying these things by 6. -6, 0, 1, 1, 4, -2. So they're still extremely strange set of numbers. But the interesting thing is that in the math that I hope we have time to get to about connected to grand unified theories, we will see that we can explain all these numbers in a really nice way in terms of, well, one way to think about it is in terms of this group SU5 that we alluded to at the beginning. Take the standard model gauge group and put it in a bigger group called SU5, that a bunch of these different particles fit into vector spaces that are on which the group SU5 acts. And that group SU5 has sitting inside it a copy of the group U1 called the hypercharge U1. And then if you just like work out what kind of representation of U1 you get, you get these numbers in it. And it's in a very elegant way, in fact.
Yeah. So okay, this might be jumping the gun because we should probably finish up the story with SU3 first. But can you repeat again how you can already see SU5 or get motivated to think about SU5 from this story? Can you just repeat that?
I don't think we can see it from just anything on this chart.
Okay.
We do need to get the SU3 in the game. But it's sort of more like a preview of coming attractions, that I'm saying that when we get into the SU5 story, and it's not too hard to do, then these numbers will be explained by that.
Oh, I see. Okay, great. Okay, that's great. So
I think I should bring SU3 into the game.
Yeah, sure. Let's do that.
And so the so I mean, quarks are funny things, and so a proton is made of 3 quarks. So very, very crudely, you can think of it like a kind of bag with these 3 things in it. But there has to be some reason why they stay in this bag and don't just like shoot off separately, because we never really see a quark by itself except under extraordinarily high temperatures situations. So people posited a force that holds these quarks together, and it's called the strong force, because it needs to be incredibly strong, because these 2 will have the same charge and they would like to repel otherwise. And it turns out that theory works out quite well, and it also winds up explaining why the protons and neutrons attract each other. So like if you have like a molecule of heavy water. It has like a heavy hydrogen in it. Heavy hydrogen has a proton and a neutron in its nucleus. So it would be a thing like this. And these two guys sort of like to stick together. So the bags don't completely form into a single bag, but they like to stick together with some kind of residual bits of force that's the same kind of force that's holding these together. And it's a long story, probably too long for us here to do in much detail, but it turns out that this theory of the strong force relies heavily on the fact that these quarks can come in, each one, the up quark and the down quark, can itself come into several states. I mean, we keep seeing this, that like when you thought there was like one particle, it turns out like there's actually different ways it can be. Like it could be isospin up and isospin down. Here, it turns out that we need these guys to be able to come in three kinds. So what we thought was the up quark can actually really have three states called, well, you needed names for three things. And so people just decided, what the heck, we'll call them red, green, and blue. It has nothing at all to do with actual colors, but it actually turns out to be a very nice metaphor.
Yeah, just like up and down were just two distinct words to label two basis vectors. Red, green, and blue are just three distinct words to label three different basis vectors. That's all it is.
Yeah. So what these guys are more really is that they're vectors in a three-dimensional vector space, and so they are just names for three basis vectors. So, for example, red is just a shorthand name for this. I guess red comes first for some reason. Green is this.
I see.
And blue is this.
It's electromagnetic spectrum ordering.
Yeah, something. Yeah, that's right.
Right.
Everyone always says RGB. Everyone, like in color theory and TV screens and stuff.
Right. It's probably the same reason. But also we should say, SU3 is the three-dimensional version of SU2. It's and this is where the verbal description of SU3 is better now than the defining equations, because it's 3x3, right, matrices that have whose columns are an orthonormal basis vector, and the determinant is 1, right? And you could of course write that out in terms of actual parameters, but it's going to get a kind of more ugly after SU2.
It's definitely more complicated. Murray Gell-Mann came up with this stuff. So that was like orthonormal rows or orthonormal columns. I forget what you said, but either one implies the other.
Yeah, that's right.
And the determinant is 1. So the S there, in case anyone is wondering, means special.
Right. And
special is some strange name for the determinant of the matrix is equal to 1, whereas U unitary, which is this stuff about the orthonormal columns.
Right. And
so once you've been indoctrinated in the code, all these letters actually mean things to you.
Yeah, and of course the 3 just means 3x3. So and SUN is just n by n, and it just
Yeah. So we may bump into SU5 pretty soon, and so that would be just like this, but with a 5x5 matrices.
Exactly. Yeah.
And so what's so in terms of the story of like what are all the particles, there are more particles than it looked like here, because actually each time I write up or down, they really come in three different kinds. Maybe I won't bother to try to cram it into the chart. But there's like an up red, up green, up blue. Mm-hmm. Same here.
So those things are actually 6-dimensional vectors, 3 times 2, because there's 3 degrees coming from the color, red, green, blue. And there's 2 coming from the, if it's left or right, then there's 2, right? So and if you consider both, then there's 4. So anyways, there's sort of like, for people who know tensors, it's really a tensor with different different components of the tensor corresponding to the different degrees of freedom, either the SU3 or the SU2.
Yeah. So it's very fun to count the number of these particles. When you're trying to figure out this particle physics stuff, or when my heroes were trying to figure it out, they had to use every possible clue they could get. So you have to even do things that seem so simple-minded as like counting them and seeing if you learn anything. So might as well do it. So 1, 2, 3, 4. Now 5, 6, 7. That's really 3 of them. 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16. I mean, you might not want to call them all different particles. It's sort of, sometimes people think of like the red, green, and blue as like 3 different states of the same particle. But I will just like say that there are like 16 particles. 16 particles in this generation of the standard model. What do you notice about the number 16, Tim?
It's a power of 2.
It's a power of 2. Yes. And then you should not laugh at these clues that nature is providing. Also, I haven't gone into it much, but all of these particles have antiparticles. Each one of them has its own antiparticle, and we really need to explain them too. So I hadn't been talking about them because they sort of just go along, they're very parallel, but they're there too. Sorry, this is not working so well.
Sure.
So really, if you count particles and antiparticles, there's 32 of them, and that's probably the right way to think about all this. Well, that's also a power of 2, unsurprisingly.
Maybe we should just say really quick, you can think of an antiparticle in representation theoretic terms. It's just the complex conjugate representation corresponding to the particle, right? So if, in general, just a particle is something that lives in a representation of some group, and then these are all complex representations, and then you can consider the representation where you just complex conjugate everything, and then that's the antiparticle.
Yeah,
right?
That's the amazing thing. And if you know a bit of math and you thought about our description of how charge works, you would, in terms of U1, you might notice or be able to guess that when you take the complex conjugate,
exactly.
You're sticking a minus sign here and how things rotate, so that winds up being the reason why antiparticles have the opposite charge of particles. So it all works out very nicely that way. So now 32 is 2 to the what, Tim?
2 to the 5.
2 to the 5. It turns out that's connected to this SU5 that's going to come and save the day, believe it or not, amazingly so. So I mean, that's like the first clue about SU5, but it's a very feeble clue. I mean, you wouldn't it doesn't get us that far. So what I want to do now is try to start talking about how you could organize this sort of bit of a mess using SU5. So I'll need more room here. Mathematicians always wish there was like an infinitely large blackboard.
Sure, that's right. So let's just take stock of what we've done. So we've described.
Yeah. You take stock while I clear the blackboard.
Yeah. So we've basically described the representation theory of the standard model as it is. You wrote 1 generation. There's actually 3. So basically, as you said, there's just two more copies. The way you would say it is that there's just 3 identical copies of this representation of the standard model gauge group, this SU3 cross SU2 cross U1. We're going to ignore the Higgs. So there's 3 copies of that. Within 1 generation, what you just enumerated was some numerology that suggests that there's something. There's a 2 to the 5th lying around.
It's very weak evidence so far. Yeah.
So I think what you're going to do now is going to talk about more evidence or motivations for why there should be an SU5, and then finally explain how SU5 can be manifested as some mathematical structure that realizes this. And as a bonus, I guess, makes hypercharge more natural. I think that's one of the features you mentioned, right?
Yeah, the hypercharge is clearly like the most chaotic. I mean, it's all like sort of chaotic, I guess, but this is like the most chaotic bunch of numbers you've ever seen. And so, so like the first selling point of the SU5 theory that's like the easiest to explain is that it makes that not seem like a mess, and it makes it seem like, oh, wow, it had to be exactly that to get SU5 to work. So the trick to SU5 is this. So we've got SU3, and we've got SU2, and we've got U1, describing the strong, the weak force, and this sort of hypercharge force. And there's a way to map this group into SU5 that's quite pretty, and it's quite, there's something tricky about it and interesting about it. So here's a group element in SU3, 3x3 matrix. Here's a group element in SU2, so that's a 2x2 matrix. Here's a group element in U1. That's just a complex number. I mean, you can think of it as a 1x1 matrix. I'll write it like alpha for some stupid reason. I think of it as like more like a good name for a number. And so, well, 3 plus 2 is 5. So it's sort of easy to see how to get a 3x3 matrix and a 2x2 matrix to sit together inside a 5x5 matrix. So we can just like go ahead and do that. So we'll put this matrix G into so I'm drawing like a 5x5 matrix, but I'm not drawing it in detail. I'm drawing this like the first 3 columns and the second, and the next 2 columns, right. The first 3 rows and the next 2 rows. And so this is a 3x3 block. I'll stick G in there and I'll stick H in there. So that would be fine and dandy. But what about this alpha? Well, see, this is sort of where the hypercharge is like found to be sneaky. You could like try to just like stick the alpha in here, just multiply G by alpha, but then this resulting 5x5 matrix wouldn't have determinant 1 anymore. G and H have determinant 1. So if you stick them in blocks like this matrix so far has determinant 1, but we've got to somehow stick the alpha in there without ruining that determinant 1 property. So like if I just stick an alpha here, I hope you don't mind quiz questions, Tim, but
not at all.
You can like delete.
Okay. No. I like it. This is a Socratic dialogue.
Yeah.
In many ways,
Okay.
Right?
Good.
Okay.
Yeah. Some people like it. Some people really hate it.
No.
So like suppose like I just said, okay, I'm gonna try to get this alpha into the game. I'll just stick it over here.
Sure.
So what would the determinant of this resulting matrix be now?
Right. Well, because G is a 3x3 matrix, right? Each row, there's 3 rows, and each row or column, or actually every entry really got multiplied by alpha. But when you look at the determinant, it's bilinear in every row or column, and because there's 3 of them, then
multilinear, I guess.
Multilinear. Yeah, sorry, not bilinear. Yeah. I meant multilinear. Yeah, multilinear in each row or column, and since there's 3 of them, then the total weight that alpha is going to get is weight 3, or in other words, the power that you get when you compute the determinant, it's going to be an alpha cubed, because each row or column is going to contribute an alpha, and there's 3 of them, so it's alpha cubed.
Yeah. So that would definitely not work. We'd get the determinant being alpha cubed instead of 1, which is what we want if we're trying to use SU5. And similarly, if you put it down here, not put it there, but only put it down here, we'd get an alpha squared mess up. And so what we want to somehow do things in such a way that the determinant stays equal to 1. So we could like put some power of alpha in here and some other power of alpha in here. We have like potentially various options for doing it. There might even be different, there probably are actually different options that might work. I'll stick an alpha in here, but I mean alpha to some power here.
That's right. Maybe we should just emphasize, because it wasn't clear, the off diagonal terms are 0, so it's
sorry, that's right. So we're not so I mean, we're like not exploiting anything about that. You could try to exploit that somehow, but I'm not going to try. So, well, okay, this is like a tougher quiz question. We want to do this the simplest way, so we don't need to like think about like all possible ways, but like what kind of power of alpha could we put here, and what kind of power of alpha could we put here that makes it all makes the determinant of the whole matrix stay 1.
Yeah, like basically you put the power such that they're gonna cancel, because I mean, one fact that we're using is that the determinant of a block diagonal matrix is the product of the determinants, right? And so when we look at the product of the determinants, we're going to get alpha to some power times 3 times alpha to some power times 2. So if we choose those powers such that the total sum is 0, then we're in business. And so it's not too hard to kind of see from this numerology that if you put, say, alpha squared at the top and alpha to the minus 3 at the bottom, then you're in business, because then you're going to get a 2 times 3 and then a minus 3 times 2.
Yeah, great. So the G and the H aren't really doing anything in this game. We could take them to be the identity, and so you get this means this times the identity matrix here. So you'd get this, and so what you said is that this 3J plus 2K has got to be, we want to try to take that to be 0, and we want to sort of not try to make life any more complicated than necessary. So we could take like let's see, I guess they're like 2 equally good choices, but because but what did you say again? I forget which one.
2 and minus 3.
So something like 2 and negative 3 would work. Would work great. Yeah, that's right.
Or minus 2 and 3 as well.
So that would also work. And I'm like busily scrambling, trying to figure out like which one that I did.
I stuck with the positive first, so just to be consistent.
Yeah. It probably won't. Well, it doesn't ultimately matter what this choice what does this choice affect that you did like 2 negative 3 versus doing negative 2 3. It'll turn out that it will just affect our choice of conventions about what is hypercharge, which is this U1 thing, so that if we change our minds about this convention, that would go along with changing our minds about the definition of hypercharge. So I don't want to go back and change this whole table here. So I'm going to try to make it come out so that that our convention here is going to get along with that. But since I don't remember ahead of time what's going to work, I'll just like go ahead, and then I may say like, oh no, we got to change it.
Okay.
So,
well, let's see. Yeah.
Yeah. Okay. I mean, that's supposed to be pedagogically interesting. I mean, that's supposed to.
Okay.
That's how people actually did it.
All right. Let's see how we're going to see the relearning process happen in real time.
Exactly. So, well, let's see. There's a little bit of shenanigans required here. So I was writing this unit complex number as alpha, but we could, if we imagined to want to write it as e to the I theta. That's like a common way, which you've already seen, to write unit complex numbers. So you could write it, but I'm gonna try to, so we get this. Well, now I'm afraid I'm gonna have to like mutter some words about Lie algebras, which luckily Tim already sort of muttered, which is that we can think of this as the exponential of some matrix, and physicists always like do e to the I times that matrix. So I'm saying that this matrix here is going to be like e to the we're going to call it e to the I times this matrix, which I'll call y hat, because it's a matrix, but y because it's this hypercharge business that we're talking about here. And so then what is this matrix? Well, it's just going to be a diagonal matrix that's going to have these numbers in it: 2, 2, 2, -3, -3. So in other words, if we include U1 in SU5 this way, and think of the elements of U1 as the exponential of some self-adjoint matrix, self-adjoint here, meaning that it has like real eigenvalues, then these eigenvalues we will call hypercharge, and there'll be hypercharges of 5 different hypercharge states. So they'll be sort of like as if they're, I mean, if that is, sorry, I should be a little clear. If this 5 by 5 matrix is acting on C5 by multiplication, matrix multiplication in the usual way, then some basis vectors, some of the obvious basis vectors in C5 are going to get multiplied by 2. So what I'm trying to sloppily argue for is that we should be like, if we have SU5 running around acting on the vector space C5, we should expect to be seeing some particles or states of particles that have hypercharge 2 and some that have hypercharge -3. So now let's go back and look. So, so we do have some -3s, and there are indeed 2 of them, which was that is the electron and the neutrino. Those are the 2 of them. So that's good. We wanted there to be two with -3. We wanted to have 3 kinds of particles with hypercharge 2. Oh no, there aren't any. But can you weasel out of it, Tim?
I suppose you could say that maybe the left and right particles there that you have, the left quarks and the right-handed electron, maybe they're actually they decompose into more fundamental particles that have hypercharge 2, because if you have 2 of them, you could get a 4, and if you have 3 of them, you can get a 6 in absolute value, and so that's I think a way you could try to force this numerology to work.
That's one type of way that people sometimes try to get these games to work out. They try to assume that the particles we're seeing are actually made up out of subparticles. Those are called preon theories. But we're not going to actually need to do anything so radical as that.
Okay.
We're gonna get this to work.
There's another way. You could say, well, if you tensor the E minus right with one of the left.
Still too fancy.
Oh,
sorry.
Okay. Okay. All right.
I'm shooting down your theories faster and faster.
Okay. So tell me what you had in mind then, because those were the 2 things I was thinking.
Okay. Well, what we're looking for things of hypercharge 2, right? And we're not seeing them. But what's the closest thing in this chart to that? Sorry, that's supposed to be like a leading question, but it may not. I mean, I'll be glad to tell you like what's going on if you get too baffled.
Yeah, I'm not sure where this is exactly.
I'll give you another clue.
Okay.
I listed the 16 particles, but I didn't actually list all the 16 antiparticles.
Oh, I see.
I just sort of said, oh yeah, and there are going to be 16 antiparticles as well.
I see. Well, you have a -2 from a particle, then you're going to have, I guess, maybe a +2 from one of the antiparticles, right?
Yeah, exactly. Because this hypercharge thing, this is like connected to representations of U1, and we've mentioned that like when you take the conjugate representation of a representation of U1. You get a different representation where the charge is negative, or in this case, hypercharge is negative what it had.
Right.
So this guy is our only hope. This guy at the bottom of the chart. And how many particles?
Yeah, I'm a little
antiparticles.
Yeah, because we have a -2 and then an antiparticle too, but we wanted 3 things that have a 2, right? So I'm not sure where we're going to get our third one right now.
Wait, how did you get? Which ones were you talking about? I just see this one here.
Yeah, but I meant in our matrix on the other slide there were 3 copies of 2, right?
Yeah, right. So we want to get 3 particles or antiparticles of hypercharge 2.
Right.
And I think what you're saying is it looks like there's just one of them.
Yeah, because you took the antiparticle of the last guy. And so
right.
You got a +2.
But I also said something else. Okay, I'm quizzing you all over the place. So I'll give it away. Remember, I said that actually there are 3 quarks of each kind. They come in 3 colors. So I should have been nicer and like drawn a full-fledged chart where I drew down red, down down blue.
You're right. Sorry, it's actually, this chart is actually so there's 3 groups here. The first doublet, the second doublet, or I guess sorry, and then the quarks. That's what I'm calling the 3 groups. The leptons, the E minuses, and the neutrinos, those all get counted once because they're colorless, right? The other ones have weight 3 each. So 16 is really 4 plus 3 times 4, right? 4 plus 12. And so there's 3 colors that we suppress in the notation. So that's the 3 colors of the antiparticle is the 3 multiplicities of 2 that we're looking for, right?
Right. Yeah, that's right.
With regards to how do we get 3 particles of hypercharge 2, now that we have all the colors written out, and now we see explicitly all 16 particles, 4 at the top and 12 in the bottom half, we see that when we take the antiparticle version of what we have here, the hypercharge -2 becomes +2, and then we have the necessary 3 colors to go along with that, right? The RGB of the down, right? So the anti-down will give us 3 particles of hypercharge 2. So that explains the y hat matrix you have on the other slide.
Right. Yeah. So we get this matrix acting on C5, and we can think of it like this: that like C5, and we can break it up into C3, which is on which that's acting, and C2, on which this block is acting. And just it's actually sort of convenient to sort of label these vector spaces by their eigenvalues. So I'm going to write like a little 2 down here to indicate that these are hypercharged 2, and then -3 here. And so what we saw is that this is like consistent with these 3 guys, sorry, the antiparticles of these 3 guys being in here. So it's a little bit long-winded to say all this stuff because so these are the antiparticles of these 3 guys, but also we should like remember that, or in theory we should remember that these are the right-handed down quarks. There are also these left-handed down ones, and so
maybe we should like the subscript L's and subscript R's. I mean,
I think that's a great idea. So it can be confusing because there's also like
maybe capital R.
Okay, maybe I'll indicate it like that. Yeah. So
there we go.
So I don't want to mix up red and right. So
exactly. Yeah.
So we have we've got those 3 guys in there, and then here we had here we had these 2 guys. Maybe it's just polite to like list the isospin up one first and the isospin down one second. I don't know if we're gonna need to know that, but anyway, that's
Sure.
That's what we've got here.
And I guess for this,
and these are left-handed guys.
yeah,
we should indicate here.
And I guess for the C3 too, we should have bars to
oh yeah, right. Sorry.
Yeah.
Yeah, so it's really complicated.
It's okay. It's ornate, but it's
it's ornate.
But the notation is exactly what it's non-ambiguous.
Right, it's ornate, but you can like read everything off right from the notation.
Mm-hmm.
Okay, so this accounts for 5 of our 32 particles and antiparticles, and maybe if I wanted to, I could sort of like check them off or something like that. They were like getting those guys there.
Mm-hmm.
But maybe that's confusing too, though, because there's the particles and the antiparticles. So maybe that's like a bad idea. But I'll maybe do it for now, just to realize that like these are the ones that we like have no clue about yet. So there's this amazing construction from that you can do to a vector space like C5, which is called taking the exterior algebra of that vector space. And if you do it, what you get is a new vector space. And if your original vector space had some dimension, like 5, then this new vector space happens to have dimension 2 to the old dimension. It happens to have dimension 2 to the 5, which is just exactly what we want, because we want it to be 32.
Yeah, maybe just say a little more.
I'm definitely planning to say more.
Yeah, okay.
We're going to need to say a lot more.
So the exterior algebra can take quite a while to describe if we were going to describe it properly. But I think for our purposes, all you need to know is the following. 2 to the 5, what's one way in 2 to the 5 can naturally occur? If you have a set of 5 elements, then the power set, that is the set of all possible subsets of that 5-element set, has size 2 to the 5. In general, if you have an n element set, then the set of all possible subsets is 2 to the n, because for each element you decide whether it's in a set or not, right? And so you could think of the exterior algebra as just the vector space that's generated by elements representing some subset of the basis elements. I think that should be enough for our purpose. I don't think we need the skew symmetry.
No, we don't really need anything much more than what you said, I think. We will need to know a few properties of it, but I think they all sort of follow from what you said.
Yeah, actually, I have my own lecture video about exterior algebra, so I can just refer people to that.
So then you can refer people to that for more details.
That's right.
So here we have 5 things forming a basis of this 5-dimensional vector space, and then any subset of this 5-element set of things will be a basis vector for this 32-dimensional vector space. And it's a little bit sad that the 5 things that we're looking at subsets of have such ridiculously complicated names. We could attempt to make shorter names for them, so that we could make up more names for, like the set of like this one, this one, this one, and this one, that wasn't like such a jaw-breakingly long expression. And we should probably do that. But while I'm busy scratching my head thinking about exactly what way I want to go there, I'll say there's like a thing that people often do, which follows from what Tim described, is that you can take this exterior algebra. So we'll think of we'll mainly focus on the basis of this algebra, which are all the subsets of these things. And when you look at all the subsets of these things, there'll be some subsets, namely 1, that has just 0 elements. So there'll be a 0-element subset, the empty set. And that will be the basis for a certain vector space, which just has 1 basis element. That's the empty set. And then the 1-element subsets will give you some more basis vectors. Those will be just these ones. We can think of these guys here as 1-element sets, so that this lambda 1 of C5 really is just the same as C5. And then it goes on, luckily not for too long, And so the part, if we're going to get this business to work, well, maybe long enough to like run off the edge of the page though, huh? You got to be careful. So they really should like make infinitely expandable
Right.
whiteboards. There's no reason why you can't do it on a computer. Okay, so yeah, so this is a good way to organize what's going on. The way, right, this is a good way to organize what's going on. Let me focus on, let me focus on lambda 0, lambda 1, and lambda 2. So why am I focusing on those three? It's because when you have any subset of your 5-element set, its complement is another subset. And if you like take the complement of a 2-element subset of a 5-element set, it'll be a 3-element subset. So there's this operation that maps lambda, the complementation that maps basis vectors of here to basis vectors of here, here to here, and here to here. And it turns out that that operation is very beautiful and sort of means that if we understand what's going on for the first 3 guys, we can sort of like figure out what's going on with the other 3 guys. And I guess I'll just, were you about to say something?
No, I just said, yeah, I mean, we might as well just write down the names just because there are people who will be familiar with it. It's just the Hodge star operator from geometry.
So it's written with a star, and it's called the Hodge star operator. And it works not just for 5, but for anything, but I'm just going to focus on the case that we care about. And it has the property that if you do it twice, you almost get back to where you started from. I guess you might get back to plus or minus where you started from in general, because of some things we haven't talked about.
Let's
I shouldn't have even said that.
Yeah, it's okay. Yeah.
But I'll just give it away that in our particular application of this idea, it would be fun to we could deduce this, but I'll just speed things up by just saying it, that it will correspond to some famous operation that you can do to a particle to get some other kind of particle that's sort of like the complement, and that's taking the antiparticle. And if you take the antiparticle, you more or less get back where you started from. So
actually, sorry, let me pause it, because there's 2 kinds of involutive or almost involutive operators. There's complex conjugation. That's involutive, because if you conjugate twice, you get back the same thing. The Hodge star is involutive up to a minus sign, which we're not going to go over. Okay, can you repeat again what you said? That you were alluding that there's maybe a relationship between the 2?
I'm not talking at all about complex conjugation, or I wasn't trying to, but you're right, there is that issue. But here we are going to have, oh wow, yeah, you're making me actually think. This is actually confusing, but here there is a linear operation. Oh, I see. I get it. So the point is that you may be like more, and I apparently am more used to Hodge star operators on real vector spaces, which is defined using a real inner product on that vector space. And those are linear. But here you define this Hodge star operator using a complex inner product, which is linear in one slot and conjugate linear in the other slot. Yeah, that winds up making this be a conjugate linear operation.
Yeah, I suspected something like that was gonna go on, and this is where like Kähler geometers do things this way, I believe, right? And
that's right.
Yeah. So
if you So we didn't need to get into this, but anyone who thought that antiparticles have something to do with complex conjugation, you're right. And this operator is not linear; it's conjugate linear.
I see. Yeah.
But we're just going to mainly focus on what it does to these basis vectors here. So we won't really be seeing much about that, but it's
Fair
really
enough.
beautiful how it all works out.
Okay.
So we're mainly going to be using it for us to like save time and just think of these first three guys and then say like, oh, the other ones are just going to be the other particles that we haven't covered yet, that we haven't gotten to yet, and hope that they're like, those are like antiparticles of ones that we already have gotten to, that like it all matches. So for example, like, I mean, I wrote down 16 things here, and they will have various hypercharges, and they will all have antiparticles. So there'll be 16 more. And we've actually already started using the antiparticles in this last row here, and they will have the opposite hypercharges. And because, I mean, it's known that the antiparticles have the opposite hypercharges, but it will also work out from the math here that it's going to all work out. So, okay, I was supposed to be trying to save time, so I'll proceed. And I'll think mainly about this lambda 2 to the C5, which is like the biggest, most exciting thing here. So let's think about this thing. So
sorry. So just to
sure.
Wrap up this conjugation business, is it the case that in degrees 0, 1, 2, or some other subset, you have the particles, and then the Hodge star will map the particles to the antiparticles?
That's a really interesting, mysterious question, because we've already seen something funny, which is that these electron and neutrino that are conventionally called particles are getting combined with the antiparticles of this quark into the same 5-dimensional vector space. So the answer basically is no. The answer is that like this thing contains a mix of what we normally call particles and antiparticles.
That's right. So it's right. The exterior algebra is not graded, or the grading doesn't respect particle or antiparticle, because the vector space itself is not homogeneous with respect to particle or antiparticle.
Yeah, so you can take this space and you could chop it up into two subspaces, which are the particle part and the antiparticle part.
Yeah, okay.
But that sort of lies askew or athwart this decomposition, which is in a pretty interesting way.
Yeah.
So what I'm trying to do here is to look at C5 and look at its second exterior power, but analyze it by using the fact that we're thinking of C5 as chopped up into these two pieces, which I'm attempting to write down here, and I keep forgetting what I'm trying to write down. I'm trying to write the hypercharge subscripts here. So that's what I want to look at, and I'm going to use a fact that we can actually understand pretty clearly, which is that the second exterior power of a direct sum of things. There's a nice little formula for it, which I'll write, and then maybe tomorrow I can like say why it works that way. It's sort of like the old formula for A plus B squared that you learn in high school. It's a lot like that, actually.
Yeah.
Well, it's also
or I think it's kind of more combinatorial, because basically the left-hand side is saying choose all possible 2-element subsets of this direct sum, and basically you can either choose 2 from V, 2 from W, or 1 from either, and that corresponds to that decomposition there. Yeah,
that's right.
Yeah.
So here in our particular case, we're choosing a 2-element subset of either a 3-element subset union a 2-element subset, and so let's just write it down and see what happens here. So here we're getting lambda 2 of C3. Now, how does I could put the 2 here, but I'd rather say like how this whole space here is a representation of the hypercharge U1. So I want to write down a number here that says like what the hypercharge of the guys in here are. Do I dare ask you what it is? So what I'm asking you mathematically is like, if I have a vector space and U1 is acting on it by like multiplication by like e to the 2I theta, and then I take its second exterior power, then like how are those numbers going to act on those?
In general, guys? The power of the exterior algebra will be the weight that you assign to that space will be
Mhm.
the product of the exterior algebra power and the original power of the vector space. So in this case, it's 2 from the exterior algebra 2 times 2 from the C3 2 to get 4.
Yeah, that's right. Another
Yeah.
way to think about it, that's like a more of a physicsy way to think about it, is that like we have these kind of particles of hypercharge 2 here. And what you can think of these as like combinations of two different particles of that kind,
Mm-hmm.
two element subset.
Right.
And so if you have like two, so very intuitively, a physicist would say, like, if you've got two particles of hypercharge 2, stick them together, you get a particle of hypercharge.
This is also clear
4.
from the representation theory picture, right?
Sure.
Because you have two things and you have something of one weight and something of another weight. Then when you multiply those exponentials, the weights add, because that's the way how you multiply exponentials. It's the exact same thing.
Yeah. So here we're going to tensor these vector spaces following this rule here.
Mm-hmm.
But then I just want to like stick a little subscript down here to say what the hypercharge of this,
Mm-hmm.
how this guy is a representation of the hypercharge U1.
Right.
So tell me what
Right.
number.
So now it's what I just said. There's an e to the 2i theta and an e to the minus 3i theta, and then when you combine that, you get an e to the minus 1i theta. So it's minus 1.
Yeah. So you get -1 here. So I mean, so far it's not obvious that anything is working unless you're like, I got a really good memory. But at the very least, you can see that like we're getting all sorts of wacky looking numbers from a
Mm-hmm.
systematic principle.
Right.
Which is cool in itself.
That's
so
right.
I mean, whether or not it works,
That's right. Right.
or at least like
right.
not making a bunch of stuff up.
Right. Right. This is all just from the representation theory of how do you map SU3, SU2, U1 into SU5.
Yeah, these numbers may look
Right.
sort of wacky themselves, but if you remember the whole
Right.
conversation, we were more or less forced into this.
That's right.
Up to
That's
like
right.
a sign.
Yeah. That's right. That's right.
So that's the beauty of this stuff.
Yeah.
What about this guy here?
Yeah. And now you get 2 times minus 3, which is minus 6.
Yeah, so you get -6. So okay. Great. Okay, well, I can't resist. So let's see. Let me see if I can remember 4, -1, and -6. So let's see if we see those
Right.
guys running around. Let's see. This is
Yeah. Indeed.
wow. Okay. So like here's a 4.
Right.
And there are 3 different particles of hypercharge 4.
Right. And that's the same dimension as lambda 2 of C2.
Great. Why does
sorry, lambda 2 of
C3.
Sorry. Yeah.
Yeah, why does that have dimension 3? You get to say, I think you can say it in terms of our
it's
subset.
Yeah, 3. Yeah, how many 2-element subsets are there of 3 elements, right? So you pick the first one, there's 3. You pick the second one, there's 2. That's 3 times 2, but the order doesn't matter. So it's 3 times 2 divided by 2, otherwise known as 3 choose 2, which is indeed is 3.
Right. So so that's working out great. That's a 3-dimensional vector space,
Mm-hmm.
and we see that it has a good candidate basis, which are these guys here, which have these horribly long
Mm-hmm.
names. Right. So they're the right-handed up quarks, and they come in 3 colors. So those are working out. Okay, now there's this guy. We're looking for things of hypercharge -1. So what's your
there's
story about this?
Let's see. Right. So it's the antiparticles of these left-handed quarks, right? Because there's 6 of these guys, and then the antiparticles will give you 6 minus 1s.
Yeah, so there's 6 particles of hypercharge 1, but their antiparticles will give us 6 particles of hypercharge -1. So we're definitely finding lots of -1s. And then the beauty is that when you take the tensor product of 2 vector spaces, their dimensions multiply. So this is a 6-dimensional space. In other words, what we're doing in these guys is we're picking 2-element sets out of a 5-element set. And in this particular kind, we're saying pick 1 out of this 3-element set and 1 out of this two element set, so you get 3 times 2 choices there. Yeah, and so those are, I can't, my memory has gone to hell in my old age here.
Yeah,
so
the left-handed ones.
These are the left-handed ups and downs. Yeah, so great. So now hypercharge -6.
Only one particle. Yeah.
Bang, there it is, standing out. I'll just
electron. Yep.
Yeah.
Yep.
I will just let's see. I'll sort of keep checking things off here.
That's right.
We have to sort of, maybe I'll like make some kind of weird check for this one because we like use the antiparticle of that one.
Okay.
So far, we get to do that when we have to, but we only have to do it like once. So far. Right. The right-handed electron, this crazy loner, hypercharged -6. So there it is. The right-handed electron. So it's really working out. Indeed. Working out quite nicely.
Right, and then we already did lambda-1. We already did and then
right. Yeah. So this.
So
yeah. You're right. You go on. Keep talking.
Yeah,
I'm just going
to say. And then lambda-0.
Right. Now, lambda-0 is very interesting. It's sort of boring, but it's sort of interesting. So lambda-0 of any vector space is just one-dimensional because you're picking out. Well, if you have like you're doing it in terms of bases here, the basis of this would be the 0 element subsets of our 5 element set.
The empty set. Yeah. The empty set is represents a vector, and therefore it's a one-dimensional space.
Yeah. So don't tell any undergraduates a sentence like that, or they'll like freak out. Then they'll freak out even more if we figure out what particle this is. Right.
All right.
Seems like we're making category errors all over the place if we're saying that the empty set is a vector, which is a particle. But that's the joy of physics.
Yeah.
So let's see. So it's a one-dimensional vector space. So it's like isomorphic just as a vector space, just to the complex numbers. But what's the hypercharge for this thing? We need to know that. That was like a key to like matching this data to our chart. So can you tell me for that one?
Yeah, I mean, it basically has to be 0, right? I don't think there's any other choice. I'm trying to think because
it is 0.
Yeah. I don't think, because I think, how do I say? Yeah, okay, actually, you could probably say this better than me. If you want things to be somehow natural or functorial, there's no other natural choice you can choose. I mean, lambda-0 is disconnected from lambda-2. You could actually assign it in this one particular case something random, but that's not going to be, I think, natural. Is that correct?
Right, but yeah, another way to think about it is that the way we got these hypercharges in the various exterior powers is by adding up hypercharges of the sort of basic building blocks here. And so like here we're adding pairs. So what we're doing in the case of lambda-0 is we're adding up nothing.
That's right.
And so we have to get 0.
Yeah,
so
I think I like this one better.
If we stick with our principles here.
Yeah. Another way of saying is that like you should really think of omega-0. If you think of the exterior algebra as an actual algebra, which we glossed over, then lambda-0 of C5 should really be the ground scalars, which it always is, and therefore it can't really have any possible weight. That's another way to think about it. Yeah,
that's right.
Yeah.
So it's in charge of this mysterious entity here.
Yeah.
It's got to be 0 mathematically. And so now we look at our chart and ta-da! Look! The right-handed neutrino, the mystery man, the particle that no one has seen. I will say, however, that there is another choice for what this. That's the obvious choice that's staring us in the face. What's the other choice we could pick? Sorry, that sounds like
the anti-right neutrino.
Yeah, the antiparticle of the right-handed neutrino, which would be the left-handed. Turns out to work. The antiparticle of a right-handed thing turns out to be let's not worry about it. But the antiparticle of the right-handed neutrino is this other one. Yeah. So they're actually this is the first case and the only case really that we've met where we have a choice of what we pick to be this thing.
Yeah. Right. Because only zero is the only number which is equal to its own negative.
Right. And also sort of zero. Yeah. I mean, if the same number had shown up like a bunch of times, we could have like more flexibility. I mean, it did show up sometimes more than once, but just enough to be to fill our needs, not more than what we needed. So this is like the first time we really had some wiggle room. I'm busy trying to think about this 6. Okay. Oh, -6. Okay. Oh, right-handed. Did I get something wrong? Yeah, -6. Okay, we did that. So that one's nailed down. Right. So here we have like 2 choices, and it turns out that there is sort of a favorite choice, but I don't think I want to get into that because I'd rather just like stick with the logic that we have here. So it's sort of interesting that we could use the right-handed neutrino, or we could use its antiparticle here. But then you see we are done in the sense that. So we could do this one, or we could use the antiparticle for this one here.
Yep.
But now everything is sort of filled up. But remember, we've only just like looked at this, and this. We have an equal. We've only used up sort of half of our exterior algebra. This has the same dimension as the half that we've handled. And so basically these are just enough to handle all the antiparticles of the ones we've covered, or in this case, like we covered an antiparticle, but we hadn't covered the particle. So it will be just enough to cover the rest.
That's right.
And then if you buy my story that the Hodge star operator is connected to taking antiparticles, then it really works out quite nicely.
Okay. I see. Because it's you said it was antilinear, then the hypercharge is reversed, and that guarantees that you're going to get those antiparticles, right?
Yeah. And also it's good to notice though that you don't have to like believe me on that. So like another thing we could do, but I just don't think we want to do because it takes a little longer, is to like look at all the 3-element
Sure, you could do the arithmetic.
Yeah. And you could work out the possible hypercharges. So you could take like a 3-element subset. It could be like 2 of this kind and 1 of that kind.
Sure. Yeah.
Let me just do a little bit. It's like 2 + 2 + -3. That would be like an option.
Right.
And so that would be 1. So that would be like one thing you'd get here. But then if you look back here, wait a minute. Did I do it? Oh, I said it. Wait.
I think that's I think that's right.
No, well, wait a minute. But we already did -1. Oh, I see. I made a mistake here.
I think your check mark should have been a
This is So I screwed up.
Yeah.
Okay. So these we actually needed the antiparticles to get -1. Yeah. So there's some little typos here. So all these actually were the antiparticles. So that's all screwed up there.
Yep.
But not in any sort of fatal way. So anyway, we get a 1 hypercharge 1 particle in here, and that's just sort of that's good because we hadn't actually gotten to those yet. So you could go on and it's nice. It just like all fits in. It all fits together perfectly. In a way, I think this is like a pretty good place to stop. Maybe we could like do the rest of the time just like talking a bit about it instead of like charging on with more more math.
I think
there's more math you could do, but this is like a pretty good
I think this
place.
is beautiful. Yeah, so I think what I like about this, and maybe you can just say just qualitatively in words, because how do I say? So I think this gives a very good sense in which a grand unified theory tries to unify things, at least at the level of representations. We're not talking about all the other things, at least at this stage yet, but sort of it comes down to a representation theoretic game in some sense, in which you try to embed your your original gauge group, SU3 cross SU2 cross U1, into something larger, and then that structure, we worked out the consequences, and it led to this pretty math. So maybe two things you could say. We mentioned earlier that there's this SO10 and Pati Salam. I think qualitatively, superficially, it's going to be something quite similar, right? Where you have another group, you have some kind of factoring of representations, essentially, and then when you look at now the representation of this other group, SO10 or SU2 cross SU2 cross SU4, you have some other structures that are foisted upon you, but fortunately you can map them in a way to the other particles. Is it a very similar story? It's just the particular details differ, but it's going to be qualitatively similar to this SU5. Is that fair?
Yeah, that's fair. I'll say a little bit about it. So what's yeah, let me just say a few things. There's like a tiny little mistake you made that not a big deal, but it sort of plays into these other things, so I'll just mention it. So it's not like exactly a mistake you made, but if someone like hung on your words too carefully, they could get confused.
All right, well, I'm here to be corrected too.
It's not a big it's not a big deal, but it's actually a very interesting deal, which is discussed a lot in this paper by John Perda and I. So we came up, you and I described this map from here to here, and it's not an embedding. It's not one-to-one. We described it, but we didn't carefully check to see that it was one-to-one. Mm-hmm. And it turns out like it's almost one-to-one, but it's actually 6-to-1.
Okay.
And so that's actually pretty interesting in itself, because what it means is that certain non-identity elements here are getting sent to here. And so if you describe particles using representations of this group, then certain non-trivial elements of this group must act trivially on those particles, because SU5 is acting trivially on those those elements of SU5 are acting trivially. So one thing that John Verden and I do when we do it like all more slowly and carefully is like start by checking the conditions required to show that the 6 elements of here that are getting mapped to the identity here are acting trivially on all of the particles in this chart. And so that's like another kind of consistency check. It might in fact somehow follow from the stuff we've done, but it has a different flavor to it because it's about finite subgroups and sort of covering group type issues that are sort of subtle that you couldn't see from the Lie algebra. So that works out.
Yeah, can you actually, it's pretty much an exercise, and it's definitely in your paper, but do you think you could write it in terms of a statement in terms of, okay, so SU3 cross SU2 cross U1 acts on, let's see, which vector space in this exterior algebra, and then it extends to the exterior algebra, and then now the result is that there's a lifting, essentially. I'm a little confused just because the particles are kind of the particles are living in some way inside the full exterior algebra that's a little. Are
you worrying about this 6-to-1 thing, or are you worried about? I forget exactly what you're talking about.
Here's what I'm trying to say. If you just forget SU5 for a second, how do you define the representation of SU3 cross SU2 cross U1 on the full exterior algebra or some subset of it?
It's pretty lengthy to say how you do that, because this is such a complicated group. So the quick way to say it is that SU5 acts on, it's to use SU5 actually. So SU5 acts on C5 in this sort of obvious way, and then
it extends.
And this is where the word functoriality comes in. Therefore it winds up acting on this exterior algebra.
Oh, I see. You're saying that. Okay, so then I think then there isn't like a nice intrinsic description of the standard model group itself, but the point is you just check that it actually factors through the SU5 representation, right?
Yeah, that's right. So we
that's
had
the
this,
theorem. Yeah.
yeah, that's right. So we had this little thing that I written down a while ago where we said like G, H, alpha is getting mapped to this thing that we worked out, which I'm probably already going to start forgetting, that we had like a G and an H here. And then let's see, this is like, am I going to get it right? Alpha squared, alpha to the -3, or is it the other way around?
Yeah, that's right. Yeah, the positive was the one first. Yeah. Okay, yeah. So the theorem is that if you do that mapping and then apply the SU5, canonical mapping, that is the same as the standard model representation.
Yeah. And so like one little cute trick is you can see that like if you work it out, you can see that like sometimes this will actually be the identity, even when not all three of these are the identity, because sometimes G will be a scalar. It'll be like a multiple of the identity.
That's right.
So, and sometimes H will be, and you can like work out when can this possibly be the identity. We do it in our paper, so I don't want to get into it, but you see that there's just like 6 possibilities. Sure. And so anyway, but yes, and you can also do the other stuff you said, which is to check that the representation of SU5 on the exterior algebra, when you compose it with this map, gives you this known standard model representation.
Okay. So I think maybe the thing you were nitpicking was this covering thing, although I don't think that makes a big deal, at least at the level of what we're talking about, right? So I think what I was trying to say is that if you now have spin 10, if you have spin 10 or SU2 cross SU2 cross SU4, you have a similar story. The right-hand group has some kind of canonical or more obvious representation, and it turns out that the composition of this horizontal map with that more kind of obvious representation reproduces the standard model representation.
Yeah. It's just your only sin was saying the word embedded, and most physicists would actually not worry about calling that because they like work with Lie algebras.
That's right. The Lie algebra would be an embedding if it's
but it's actually sort of cool that so what I emphasize in our paper is that it's not, people say this is the group of the standard model, but it has these 6 elements that act trivially on everything in the standard model. So it's really this modulo, this kernel, which is like what we call the true gauge group of the standard model. Now that's a subtle thing. Now the SO10, or I will call it spin 10 model is very nice because there's a general fact that you can always map, which I don't want to get into any more than necessary, that you can always map SUN into spin 2n. There's a standard procedure for doing this.
That makes sense. Yeah, for the experts in the room, basically, so spin whatever is the double cover of the corresponding SO whatever. So spin 2n is the double cover of SO 2n. And of course, by just identifying a complex vector space, forgetting the complex structure, you get a real vector space of twice the dimension. So of course you can map SUN to SO2n, and then by algebraic topological reasons, because SUN's simply connected.
You're good. You're doing it all on the fly. Okay, that's great. Yeah, that's exactly right. And then there's this beautiful fact, which is like a slightly further fact, which is so SUN is always acting on CN. And it also, therefore, is acting on this exterior algebra, lambda of CN. And that we've done the case for n equals 5, but because we're mathematicians, I'm suddenly deciding to, heck, let's do it for any old n. And we've seen in our example that as a representation of SUN, this breaks up into a bunch of pieces. Actually, these pieces actually turn out to be like irreducible representations of SU5 for what it's worth. Not that that matters, but it breaks up into these pieces. But the cool part is that when you look at how, the cool part is that spin 2n also acts on lambda c to the n. So this is getting a little less obvious. because this, this is some bigger group that's including the group that we had, and it's not so obvious how this is acting here, but it does act on it, and it acts on it in an irreducible way. It acts on it. Let's see, is that true? Almost an irreducible way. It actually acts on it in a way where it breaks up into just two pieces. And those two pieces, in our case, what they are is the particles and the antiparticles. So what I'm saying is one of these 16-dimensional spaces becomes completely unified as a single irreducible, unbreakable representation of spin 10.
Okay.
And then there is its conjugate representation, which is the antiparticles. And those two, and mathematically, that's coming from the fact that spin 2n has a representation on this that just breaks up into two pieces that are switched by this Hodge star operator. So it's like, this is like an incredibly unified story, whereas SU5 was less unified. So a lot of people, after they learned about the SU5 model, they started getting interested in the spin 10 model. In our story so far, you could say like, oh, there's no, in the SU5 story, you could say, oh, but there's no right-handed neutrino. So we'll just like leave this out and also leave this one out. That would be like incredibly irritating that you have like this beautiful structure and like you leave out these two pieces, but it would be a mathematically consistent thing. It would still be a representation of SU5. Right. But when you go to spin 10, you just cannot do that. You cannot leave them out. So this 10 theory, in other words, predicts the existence of the right-handed anti-neutrino. And so a lot of people actually believe that it exists, and they've like done other physicsy things to calculations to try to like see if they can like explain other things with it. And there's quite a nice story about how it could like solve some other mysteries. The Patti-Salam model is not, it's not really quite so elegant and nice in some ways. But I'll say one thing about it, which is interesting, which is, so the Patti-Salam group, which you could think of as like SU2 times SU2 times SU4. I mean, that's what it is. I was just like debating which order to write the twos and the fours. That's what I meant, Kenny. So it's a subgroup of spin 10, as is SU5. And it turns out that there is a map from the standard model group into this group as well. And don't ask me what the kernel is because I forget, but it's finite to 1. There may be a little business like this going on, but it makes this diagram commute. So if I'd been really organized, I would have drawn this as a commutative square where the standard model group is mapped to both the SU5 and the Patti-Salam, and then they're both mapped into the spin 10.
Yeah, I should say this is super beautiful in the sense that, prior to this, I've never thought about grand unified theories. It turns out there are 3 well-known proposals. We just presented them right here, and I don't think it's well-known at all that the 3 fit into this nice commutative diagram. I guess maybe I was talking to you before the recording that I guess maybe some experts might know it, but physicists don't think in terms of this clean language. So I think this is a genuinely nice result, not only to prove, but to make more well known. Is that right?
Yeah, thanks. So we thought, John Baird and I thought that as a kind of payoff for the mathematicians who are learning about the grand unified theories from our expository paper, we should like do something that's not so well known and lead up to a commutative square of physical theories, which is the type of thing that physicists don't tend to talk about as much. They're not so keen on, I mean, they're getting to be keen on it, but they don't just naturally talk about commutative diagrams of physical theories. And so it's really beautiful, that these proposals, which were not, I mean, I think it was known that spin 10 included SU5, and it was probably known that this included spin 10, but they didn't people didn't generally tend to think of it as in these terms. And we state some things about this commutative square that sort of show like why it's interesting in a number of ways.
Yeah, this is beautiful. I think this is maybe a great place to stop. Maybe just one more question. I can't help myself, but
sure.
One of the reasons why this is maybe for you a speculative topic that you're not maybe too comfortable talking about is that we've only limited ourselves to the representation theory aspects of these grand unified theories. We basically said nothing about the physics. Can you say, at least at a high level, what those ingredients looks like? I know one aspect that you mentioned is this issue of spontaneous symmetry breaking, because if you have these larger groups, for example, somehow they would have their attendant predictions, but we don't see them at the lower energy scales that we bump into. We see SU3 cross SU2 cross U1. That has to do with this symmetry breaking. So you have to somehow go to higher energy, say at the LHC or well beyond, to sort of see these grand unified structures. That's why they're very speculative, because we haven't gotten to those energies. Can you say anything about the physics? So this is what I don't understand. Why is it the case that only at high energies do you kind of see unification versus at lower energies, right?
Sure.
Maybe the analogy is, you have these like whatever Mexican hat potential, and you're just like at this little corner, and somehow you kind of like naively think that everything's disjoint, whereas they're actually unified if you could zoom out more. But that seems a little bit too much of a cartoon for me. But like, really, can you say a little bit more about what's going on?
Yeah, sure. So one thing is to notice that, that you probably know, but our listeners should know, is that when you actually look at really low energies, like ordinary household energies, this SU2 times U1 group is not noticeable at all. What you notice is not this mysterious hypercharge thing and isospin stuff. What you notice is ordinary electric charge. And I've sort of started out talking about electric charge and went away from it. Electric charge can be described by some other U1 subgroup sitting inside this group, but not this U1, but some funny U1 that sort of spirals around both of these. And so already in that case, we have this situation where we have this larger group, but at low temperatures or low energies, we don't see that group in play directly. What we see is the SU3 and the charge U1. And the beauty of the standard model is that it reconciles that apparent conflict by positing this particle called the Higgs boson. And the Higgs boson interacts with the SU2 and the U1 force in such a way that at low energies, it makes the different directions in the SU2 Lie algebra act very different from each other, because the Higgs boson is like settled it down to some particular state, which is picking out a particular vector in the representation of this group here. And because it's picked out that particular direction by minimizing energy, it means that that direction is not symmetrical under this whole group. It's only symmetrical under this U1 charge subgroup. It's a very long story, but that's like the most interesting aspect of the standard model. And that's why everyone was so eager to actually make sure, 100% sure, that the Higgs boson really existed and to check that it was working as advertised. But even before people knew for sure that that Higgs was working, that pattern of doing physics became popular. And so when people began positing larger groups, the way they would sort of have their cake and eat it too, to have this larger symmetry group, but have it not be visible at low energies, is by positing extra kinds of Higgs bosons, completely different other kinds of Higgs bosons, but they're still called Higgs bosons because it's the same mechanism. whereby they at low energies would pick out certain directions in these in the Lie algebras of these groups as special, and thus break the symmetry down to a smaller group. So when you make up this SU5 theory, we've been like doing all the easy part of like saying like, hey, the particle hypercharges seem to match and so on. But then the hard part, the real work of doing the physical theory, is positing the correct type of Higgs bosons and the correct type of interactions of the Higgs bosons with the SU5 forces, such that at low energies, all you see is this subgroup. That is, the vector that the Higgs picks out is only invariant under this subgroup. And it turns out that, and that story goes on with these larger groups. So the bigger group you get, the more Higgs bosons you need to posit to break it down the symmetry to what we see at low energies. And it turns out that like when you get to a fairly large group like spin 10, there are various choices you could make for how those Higgs bosons, what those Higgs bosons could be. And then those different, so you really have different theories because there are different choices of how the Higgses work.
Just to clarify what you just said, so going back to the center model itself, right, at low energies, basically, so you have this group, the Higgs is such that the stabilizer of that corresponds to the photon, which is why it's massless, and you get a quotient space which doesn't stabilize the Higgs, and that's what you get these massive particles, right? And you're saying, I think,
yeah, so the W and Z particles are, so this is like a three-dimensional Lie algebra. One basis vector in it is called the photon, and it is massless, but the other two are,
there's four.
The other three are called the W plus, the W minus, and the Z, and those are very massive. They have masses sort of roughly in the neighborhood of the Higgs, although lighter, and they were actually discovered fairly late, but before the Higgs. And once we discovered those, then like everyone with any optimism knew that the thing was working. Yeah,
I see. So for all these other grand unified theories, would you basically have a zoo of massless particles because they would have a huge stabilizer, and then you're what you need to show is that that's when you take this larger gauge group and mod by the stabilizer, you get back sort of the usual massive particles at low energy.
That's right. And you would, so we haven't really been talking about the force particles for most of our talk. Now, all of a sudden, we are starting to talk about things like the photon and the W and the Z. So when you get to a Lie group like this is 10 times 9 over 2 dimensional. So it's a 45 dimensional group. So it has 45 gauge bosons, 45 force carrying particles, some of which will be the ones that we've actually seen so far, which are the ones that live in this, the Lie algebra of this subgroup, but there'll be like wads of other ones. And those other ones, well, to explain the fact that we haven't seen them, they'd better be massive. And the way we do that is we make them interact with extra Higgs bosons, just like we made the W and the Z massive in this story. And so, yeah, so there are sort of representation theoretic choices about how your Higgs boson should transform as a representation of spin 10. So those are sort of like discrete or algebraic choices you have to make about the story. But then there are also choices of coupling constants, actual numbers, which you want to make sure that all the numbers work out, like that the masses of these extra gauge bosons are high enough that we haven't seen them yet, but that the masses of the gauge bosons we have seen are what we observe them to be.
Okay, I see. Okay, I think I said something a little bit opposite, but which is that I originally said, oh, I want a large stabilizer. I want all these massive particles. You're saying no, actually, you want a bunch of massive particles that are so massive that's why you haven't seen it. But basically, everything else is kind of the same. You have some Higgs that breaks symmetry, and then the issue is that the way in which it breaks the symmetry is such that you need to have very massive particles for the ones that need to exist but you haven't seen, and then also reproduce the massive particles that you have seen. So that's like the hard part.
Yeah, that's the hard part.
Yeah.
Until you introduce the Higgses, all the gauge bosons are massless. So we would have like wads of photon-like, well, or photon or gluon-like things. And so we need the Higgses to
Got it.
just to make them go away, sweep them under the rug, but also more importantly in a way, or also just as importantly to break the symmetry group down to the smaller one that we actually see.
Great. Yeah. All right. Thank you. That was
Sure.
very, very enlightening. Yeah, it's so great to have this talk. We definitely covered a lot, and I certainly learned a lot. And thank you so much, for your time and enthusiasm.
Yeah, that was a lot of fun. Thanks a lot.
Yeah, great. All right. Well, thank you, everyone, and have a good one.